Hey there, welcome to the Night Scientist of Discovery. I'm so incredibly happy you've decided to join me today. You know, there's something truly magical about taking a moment to slow down and explore the wonders that surround us every single day. In our busy world, we often rush past the most extraordinary phenomena without even realizing they're there, quietly working their magic in the background of our lives. Today, I want to invite you to settle somewhere comfortable, maybe with a warm cup of tea or coffee, and let's embark on a gentle journey together. We're going to explore one of the most fascinating and comforting mysteries of our universe, something so fundamental that it affects every breath you take, every step you walk, and every moment you exist on this beautiful planet we call home. So, take a deep breath, let your shoulders relax, and prepare to be amazed by the incredible story that unfolds beneath your feet and all around you, every single second of every single day. Today, we are diving into the fascinating world of how Earth keeps its balance while spinning. It's a story that begins billions of years ago and continues right now, as you're reading these very words. You see, our planet is performing the most elegant and complex dance in the cosmos, spinning through space at incredible speeds, while maintaining the perfect balance that keeps us all safe and sound. This isn't just a story about physics and forces, though we'll gently explore those too. It's a story about harmony, about the delicate interplay of countless factors that come together to create the stable, nurturing world we call home. So let's begin this journey together, starting with the very basics of Earth's incredible spinning. Dance. Imagine, if you will, a giant dancer spinning gracefully through the vast darkness of space. This dancer is our Earth, and she's been performing this magnificent dance for over 4.5 billion years, without ever missing a step. Picture yourself standing in your backyard on a clear night, looking up at the stars. What you might not realize is that at that very moment, you're traveling through space at an absolutely mind-boggling speed. The ground beneath your feet is spinning at roughly 1,000 miles per hour at the equator, carrying you along on the most incredible ride in the universe. And yet, you don't feel dizzy. You don't feel like you're moving at all. Your coffee doesn't spill, your dog doesn't slide across the yard, and the birds continue to fly effortlessly through the air. This is the first hint of Earth's remarkable ability to maintain perfect balance while spinning. Think about trying to balance a coin on your finger while you're running full speed. It seems impossible, doesn't it? Yet our planet manages something far more complex with seemingly effortless grace. Earth's rotation is like a cosmic gyroscope, and gyroscopes have a fascinating property. They resist changes to their orientation. When a gyroscope is spinning, it wants to keep spinning in the same direction, on the same axis. This is due to something called angular momentum, one of the most fundamental principles in physics, and one that governs everything from spinning tops to massive planets. But Earth's spin isn't just about angular momentum. Our planet is like a massive, complex spinning top with an intricate internal structure. Unlike a simple toy top made of uniform material, Earth has layers, a solid iron core surrounded by a liquid outer core, all wrapped in a thick mantle of hot rock, and finally covered by a thin crust where we live our daily lives. Each of these layers has its own density, its own properties, and its own role to play in the grand dance of rotation. The solid inner core, about the size of the moon, spins at a slightly different rate than the rest of the planet. It's like having a spinning ball inside a spinning ball, creating a complex system of rotational forces that somehow work together in perfect harmony. Now, you might wonder why Earth keeps spinning at all. After all, when you roll a ball across the floor, it eventually stops due to friction. But here's the beautiful thing about space. There's no friction. Earth began spinning during its formation billions of years ago, when countless pieces of cosmic debris collided and merged to form our planet. All that colliding material brought angular momentum with it, and since there's no friction in the vacuum of space to slow it down, Earth just keeps spinning. The consistency of this spin is truly remarkable. Earth completes one full rotation approximately every 23 hours, 56 minutes, and 4 seconds. This isn't exactly 24 hours. That's actually how long it takes for the sun to appear in the same position in the sky, which is slightly different due to Earth's orbital motion around the sun. But the point is, this rotation is incredibly stable and predictable. What makes this stability even more impressive is the sheer size and mass of what we're talking about. Earth weighs approximately 6 billion trillion kilograms. That's a 6 followed by 24 zeros. Imagine trying to spin something that massive and keep it balanced. The amount of energy contained in Earth's rotation is staggering. If we could somehow harness all of that rotational energy, it would power human civilization for millions of years. But here's where the story gets even more fascinating. Earth's rotation isn't just about the planet spinning in isolation. Our planet is part of a complex gravitational dance with the moon, the sun, and even the other planets in our solar system. Each of these celestial bodies exerts gravitational forces on Earth, and these forces could potentially disrupt our planet's stable rotation. The moon, for instance, is constantly tugging at Earth with its gravitational pull. This pull creates the tides in our oceans, but it also creates what we call tidal forces on the solid Earth itself. The planet actually bulges slightly toward the moon, and this bulge travels around Earth as the moon orbits. You might think this would cause Earth to wobble like a washing machine with an unbalanced load. But instead, our planet maintains its steady rotation. The sun, too, exerts its gravitational influence. It's much more massive than the moon, but it's also much farther away. The sun's gravity creates its own tidal forces on Earth, though they're weaker than the moon's. The fascinating thing is that these forces from the sun and moon sometimes work together and sometimes work against each other, creating a complex pattern of gravitational influences that Earth must somehow navigate while maintaining its balance. Even the other planets play a role, though a much smaller one. Jupiter, with its massive gravitational field, creates tiny but measurable effects on Earth's rotation. Mars, Venus, and all the other planets contribute their own minuscule influences. It's like Earth is dancing not just with one partner, but with an entire cosmic ensemble, each member contributing to the choreography. What's truly amazing is that despite all these external influences, Earth's rotation remains remarkably stable. The length of our day varies by only tiny fractions of a second over years and decades. This stability is crucial for life as we know it. If Earth's rotation were erratic, we would experience wild swings in day and night length, extreme weather patterns, and gravitational anomalies that would make life incredibly difficult, if not impossible. The atmosphere plays its own role in this cosmic dance. Our planet's thick blanket of air isn't just sitting there passively, it's part of the rotating system. The atmosphere rotates with Earth, but it also has its own complex circulation patterns. High pressure and low pressure systems, jet streams, and weather fronts all represent moving masses of air that affect Earth's rotation in subtle but measurable ways. During major storms, when vast amounts of air are set in motion, the distribution of atmospheric mass changes. This can actually affect the length of Earth's day by tiny amounts, usually just a few milliseconds. It's like when a figure skater pulls their arms in to spin faster, or extends them to slow down. When the atmosphere's mass distribution changes, it affects the planet's rotation speed. The oceans, too, are part of this rotating system. The vast bodies of water that cover most of Earth's surface are constantly in motion, driven by tides, currents, and temperature differences. These moving masses of water represent enormous amounts of angular momentum, and they interact with Earth's rotation in complex ways. Ocean currents, like the Gulf Stream, carry tremendous amounts of water across vast distances. When these currents speed up or slow down, when they change direction or intensity, they affect Earth's rotation. The El Niño and La Niña weather patterns, which involve changes in ocean temperature and current patterns across the Pacific Ocean, can actually cause measurable changes in the length of Earth's day. Even the ice caps and glaciers are part of this system. As ice melts or accumulates, as glaciers flow and change, the distribution of mass on Earth's surface changes. This affects the planet's moment of inertia, essentially. How the mass is distributed relative to the axis of rotation changes. In moment of inertia directly affect rotational speed. Just like the figure skater example, in recent decades, climate change has been causing ice to melt at the poles and redistribute as water in the oceans. This is actually affecting Earth's rotation in measurable ways. The melting of glaciers and ice sheets is causing a tiny but detectable slowing of Earth's rotation, because the mass is moving from the poles closer to the axis of rotation to the equator farther from the axis. But Earth has mechanisms to maintain its balance despite all these changes. The planet's rotation is stabilized by its own internal structure and dynamics. The liquid outer core, for instance, generates Earth's magnetic field through a process called the geodynamo. This involves complex flows of molten iron that create electrical currents, which in turn generate magnetic fields. These flows in the outer core are influenced by Earth's rotation, and they also influence the rotation in return. It's a delicate feedback system where the planet's spin affects the core's motion, and the core's motion affects the planet's spin. This creates a kind of self-regulating system that helps maintain rotational stability. The solid inner core adds another layer of complexity. Because it's solid, it can rotate at a slightly different rate than the rest of the planet. Scientists have discovered that the inner core rotates about 1 degree per year faster than the surface. This differential rotation creates additional forces and torques within the planet that contribute to overall rotational stability. All of these factors, the gravitational influences of the moon and sun, the movement of the atmosphere and oceans, the changing ice caps, the dynamics of the core, work together in an incredibly complex system. Yet somehow Earth manages to maintain its steady rotation, its stable axis, and its predictable day-night cycle. It's like watching a master juggler who's not just keeping multiple balls in the air, but doing it while riding a unicycle in a windstorm while the ground is moving beneath them. The complexity is staggering, yet the performance appears effortless in the quiet depths of space. Our planet performs a balancing act so sophisticated that it makes the most skilled tightrope walker look like a beginner. But what exactly keeps Earth from tumbling end over end through the cosmos? To understand how Earth maintains its balance, we need to delve deeper into the concept of gyroscopic stability. Imagine you're riding a bicycle, When you're moving slowly, the bike feels wobbly and unstable. But as you pick up speed, something magical happens. The bike becomes more stable, easier to balance. This is gyroscopic effect in action, and it's one of the key principles that keeps Earth steady in its rotation. A spinning bicycle wheel, just like our spinning planet, has what physicists call angular momentum. This is a measure of how much rotational motion an object has, and it depends on both how fast something is spinning and how its mass is distributed. The beautiful thing about angular momentum is that it's conserved. It doesn't just disappear. This means that once something is spinning, it wants to keep spinning in the same direction. Earth's enormous mass and its 24-hour rotation give it tremendous angular momentum. To put this in perspective, if you could somehow grab Earth and try to tilt it, you'd need to apply a force so enormous that it's beyond human comprehension. This gyroscopic stability is what keeps our planet from tumbling chaotically through space. But stability doesn't mean rigidity. Earth's rotational axis does move, but it moves in very specific, predictable ways. One of these movements is called precession, and it's like the wobble you see in a spinning top as it slows down. However, Earth's precession is much slower and more regular. Our planet's axis traces out a circle in space over a period of about 26,000 years. This precession is primarily caused by the gravitational pull of the Sun and Moon acting on Earth's equatorial bulge. You see, Earth isn't a perfect sphere. It's slightly flattened at the poles and bulges at the equator due to its rotation. This bulge creates what's called a gravitational torque when the Sun and Moon pull on it, causing the slow, steady precession of Earth's axis. Think of it like this. If you have a spinning top that's perfectly balanced, it will spin in place. But if the top is slightly off balance, it will wobble or presses it. Earth's equatorial bulge creates a similar effect. But instead of causing instability, it creates a very slow, very regular wobble that actually contributes to the planet's overall stability. There's also something called nutation, which is an even smaller wobble superimposed on the precession. If precession is like the slow wobble of a spinning top, nutation is like a tiny shake or vibration on top of that wobble. It's caused by the changing gravitational influences of the Sun and Moon as they move in their orbits. The Moon's orbit isn't perfectly circular, it's slightly elliptical, which means the Moon is sometimes closer to Earth and sometimes farther away. When it's closer, its gravitational pull is stronger, and when it's farther away, the pull is weaker. This creates a rhythmic variation in the gravitational forces acting on Earth, which shows up as nutation in our planet's rotation. Remarkable is that both precession and nutation are incredibly small and slow. The precession cycle takes 26,000 years, and the nutation is measured in tiny fractions of degrees. These movements are so subtle that they have no noticeable effect on daily life. Yet they're precisely predictable and contribute to Earth's overall rotational stability. Another fascinating aspect of Earth's balance is how it deals with changes in mass distribution. Remember how we mentioned that melting ice caps and changing weather patterns can affect Earth's rotation? The planet has a built-in mechanism to handle these changes. The conservation of angular momentum when mass moves closer to Earth's axis of rotation, the planet spins faster, just like a figure skater pulling their arms in. When mass moves farther from the axis, the planet spins slower, like the skater extending their arms. This automatic adjustment helps maintain the planet's rotational stability, even as mass is redistributed across its surface. The atmosphere and oceans are constantly moving, creating ongoing changes in mass distribution. Yet these changes are generally small and gradual, allowing Earth's rotation to adjust smoothly. It's like a well-tuned system with built-in shock absorbers that can handle the bumps and variations without losing overall stability. But what about more dramatic changes? What would happen if, say, a massive asteroid struck Earth? Throughout our planet's history, there have been major impacts that changed the mass distribution significantly. The impact that created the Moon, for instance, was so massive that it knocked a huge chunk of material off the early Earth. Such events can indeed affect Earth's rotation, but the planet's enormous angular momentum means that even catastrophic impacts typically cause only small changes in the overall rotation. The impact that killed the dinosaurs 66 million years ago was enormous by human standards, but it barely affected Earth's rotation. The planet's gyroscopic stability is just that robust. The role of the Moon in stabilizing Earth's rotation cannot be overstated. Our unusually large Moon creates tidal forces that act like a stabilizing flywheel. The Moon's gravity not only creates ocean tides, but also causes the solid Earth to bulge slightly toward the Moon. This tidal bulge acts as a kind of gravitational anchor, helping to maintain Earth's rotational stability. Without the Moon, Earth's rotation would be much less stable. The planet would experience much larger variations in its axial tilt, which would lead to extreme climate changes. Some scientists believe that the Moon's stabilizing influence was crucial for the development of complex life on Earth, because it helped maintain the stable climate conditions necessary for evolution. The Sun also plays a role in Earth's stability, but in a different way. The Sun's gravity creates its own tidal forces on Earth, though they're weaker than the Moon's. However, the Sun's influence is more complex because Earth orbits around it. This orbital motion creates additional forces and torques that interact with Earth's rotation in subtle but important ways. One of the most fascinating aspects of Earth's stability is how it handles the complex gravitational dance with multiple celestial bodies. The Moon orbits Earth, Earth orbits the Sun, and the whole solar system is moving through the galaxy. Each of these motions creates its own set of forces and influences, yet somehow they all work together to maintain Earth's stable rotation. It's like a cosmic symphony where every instrument must play its part perfectly for the harmony to work. The Moon provides the steady rhythm, the Sun adds the underlying bass line, and the other planets contribute their own subtle notes. Together, they create a gravitational environment that allows Earth to maintain its steady rotation. The internal structure of Earth also contributes to its stability. The planet's core is incredibly hot, about as hot as the surface of the Sun, and this heat drives convection currents in the molten outer core. These currents are influenced by Earth's rotation and the planet's magnetic field, creating a complex system of internal dynamics. These internal motions might seem like they would disrupt Earth's rotation, but instead they contribute to its stability. The convection currents in the outer core help distribute heat evenly throughout the planet, preventing the kind of thermal imbalances that could affect rotation. The magnetic field generated by these currents also helps protect Earth from external influences like solar wind that could potentially affect the planet's rotation. The solid inner core adds another layer of stability. Because it's solid, it rotates slightly differently than the rest of the planet, but this differential rotation is regular and predictable. It's like having a gyroscope within a gyroscope, creating multiple levels of rotational stability. Even the continents play a role in Earth's balance. The slow movement of tectonic plates represents a redistribution of mass on Earth's surface, which affects the planet's moment of inertia. When continents move toward the equator, they're moving farther from the axis of rotation, which tends to slow Earth's rotation slightly. When they move toward the poles, the opposite happens. These changes are incredibly slow. Continents move at about the same rate your fingernails grow, but over millions of years, they can have measurable effects on Earth's rotation. The planet adjusts to these changes through the conservation of angular momentum, maintaining its overall stability even as the surface slowly rearranges itself. The fascinating thing is that all of these factors, the moon's gravity, the sun's influence, the internal dynamics, the movement of continents, the circulation of the atmosphere and oceans, work together in a complex system that somehow maintains Earth's rotational stability. It's a testament to the elegant physics that governs our universe, where complex systems can achieve remarkable stability through the interplay of multiple forces and influences. Beneath the surface of our seemingly steady world, invisible forces are constantly at work, fine-tuning Earth's rotation with the precision of a master clockmaker. These hidden influences shape everything from the length of our days to the stability of our climate. Deep within Earth's core, about 1,800 miles beneath your feet, something extraordinary is happening. In a region hotter than the surface of the sun, liquid iron is flowing in complex patterns, creating electric currents that generate our planet's magnetic field. This process, called the dynamo, is one of the most important hidden forces affecting Earth's rotation. The dynamo is like a vast, invisible engine powered by Earth's rotation itself. As the planet spins, the liquid iron in the outer core is set in motion by the Coriolis effect, the same force that causes hurricanes to rotate. These flowing currents of molten metal act like wires in a giant dynamo, generating electrical currents that create Earth's magnetic field. But here's the fascinating part. This magnetic field, in turn, affects Earth's rotation. The flowing currents in the outer core create their own angular momentum, and this momentum is coupled to the rest of the planet through magnetic forces. When the flow patterns in the core change, they can actually affect the length of Earth's day by tiny amounts. Scientists have discovered that changes in Earth's magnetic field correspond to changes in the length of day. When the magnetic field weakens, Earth's rotation tends to slow down slightly. When it strengthens, the rotation speeds up. These changes are incredibly small. We're talking about variations of just a few milliseconds, but they're measurable and predictable. The solid inner core adds another layer of complexity to this system. It's like a massive metal ball floating in the liquid outer core, and it rotates at a slightly different rate than the rest of the planet. This differential rotation creates additional magnetic forces and torques that contribute to the overall dynamics of Earth's rotation. Recent studies have shown that the inner core's rotation rate can vary over time. Sometimes it rotates faster than the surface, sometimes slower. These variations are linked to changes in the magnetic field and the flow patterns in the outer core. It's like having a complex mechanical system where every component affects every other component. The beautiful thing about this system is that it's self-regulating. When changes in the core start to affect Earth's rotation, the rotation changes feed back into the core dynamics, creating a natural stabilizing effect. It's like having a thermostat that automatically adjusts to maintain the desired temperature. Except in this case, it's maintaining rotational stability. Above the core, the mantle, a thick layer of hot rock that makes up most of Earth's volume, plays its own role in the planet's rotational balance. The mantle is solid, but it's hot enough to flow very slowly, like thick honey. This flow, driven by heat from the core, creates convection currents that move at speeds of just a few centimeters per year. These slow-moving currents in the mantle affect Earth's rotation in subtle but important ways. When hot material rises from deep in the mantle, it carries angular momentum with it. When cool material sinks, it takes angular momentum downward. These vertical movements of material create torques that can affect the planet's rotation. The mantle also responds to changes in Earth's rotation. When the planet's rotation rate changes, even slightly, it affects the forces acting on the mantle. This can change the convection patterns, which in turn affect the planet's internal heat distribution and geological activity. At the surface, the movement of tectonic plates represents another hidden force affecting Earth's rotation. As plates move, they redistribute mass across the planet's surface. When a plate moves material toward the equator, it's moving mass farther from the axis of rotation, which tends to slow Earth's rotation. When material moves toward the poles, it speeds up the rotation. These effects are cumulative over long periods of time. The configuration of continents millions of years ago was very different from today, and this affected Earth's rotation rate. When most of the land was concentrated in a single supercontinent near the equator, Earth's rotation was slightly slower than it is today. Earthquakes provide dramatic examples of how sudden changes in mass distribution can affect Earth's rotation. When a major earthquake occurs, it can move massive amounts of rock and soil, changing the planet's moment of inertia. The 2011 earthquake and tsunami in Japan, for instance, moved so much material that it shortened Earth's day by about 1.8 microseconds. While this might seem like a tiny change, it demonstrates the incredible sensitivity of Earth's rotation to mass redistribution. The planet is so finely balanced that even relatively small changes in mass distribution can have measurable effects on its rotation. The atmosphere represents another hidden force constantly affecting Earth's rotation. The air around us might seem insubstantial, but the atmosphere has significant mass, about 5.5 quadrillion tons. As this enormous mass of air moves around the planet, it affects Earth's rotation through the conservation of angular momentum. Weather patterns represent massive redistributions of atmospheric mass. When a high-pressure system develops, it represents a concentration of air mass in one region. When it moves, it carries angular momentum with it. The jet streams, rivers of fast-moving air in the upper atmosphere, carry enormous amounts of angular momentum as they meander around the planet. Seasonal changes in weather patterns create predictable variations in Earth's rotation. During winter in the northern hemisphere, the jet streams tend to be stronger and more active, carrying more angular momentum. This affects Earth's rotation in measurable ways, creating seasonal variations in the length of day. The El Niño and La Niña phenomena provide excellent examples of how atmospheric changes can affect Earth's rotation. During El Niño events, changes in atmospheric circulation patterns over the Pacific Ocean can change the length of day by as much as a millisecond. These effects are temporary, but they demonstrate the intimate connection between atmospheric dynamics and Earth's rotation. The oceans, too, represent hidden forces constantly affecting Earth's rotation. Ocean currents carry tremendous amounts of water across vast distances, and this moving water has angular momentum. When currents speed up, slow down, or change direction, they affect Earth's rotation through the conservation of angular momentum. The Gulf Stream, for instance, carries about 30 times more water than all the rivers in the world combined. This massive current system affects Earth's rotation as it flows northward along the eastern coast of North America. Changes in the Gulf Stream's strength or position can create small but measurable changes in Earth's rotation rate. Ocean tides represent another fascinating example of hidden forces at work. The gravitational pull of the Moon and Sun creates tidal bulges in Earth's oceans. But these bulges don't stay perfectly aligned with the Moon as it orbits. Due to friction and the complexity of ocean basins, the tidal bulges lag slightly behind the Moon's position. This lag creates a torque that gradually slows Earth's rotation while simultaneously pushing the Moon into a higher orbit. The effect is incredibly small. Earth's rotation is slowing by about 2.3 milliseconds per century, but it's measurable and predictable. Over billions of years, this tidal friction has significantly affected both Earth's rotation and the Moon's orbit. The changing ice caps and glaciers represent another hidden force affecting Earth's rotation. Ice sheets like those in Greenland and Antarctica contain enormous amounts of water. When these ice sheets melt, the water flows into the oceans, changing the distribution of mass on Earth's surface. During ice ages, when much of the world's water was locked up in glaciers near the poles, Earth's rotation was slightly faster because more mass was concentrated near the axis of rotation. As the ice ages ended and the glaciers melted, redistributing water to the oceans, Earth's rotation slowed slightly. Today, climate change is causing accelerated melting of ice sheets and glaciers, and this is affecting Earth's rotation in measurable ways. The melting of the Greenland ice sheet, for instance, is causing a tiny but detectable slowing of Earth's rotation as water flows from the pole toward the equator. Even groundwater plays a role in Earth's rotation. When groundwater is pumped from aquifers for irrigation and other uses, it represents a movement of mass that can affect the planet's rotation. Large-scale groundwater depletion in certain regions has been linked to small changes in Earth's rotation rate. The fascinating thing about all these hidden forces is how they interact with each other. Changes in one system can affect others, creating complex feedback loops. For instance, changes in Earth's rotation can affect atmospheric circulation, which can affect ocean currents, which can affect the distribution of heat around the planet, which can affect ice melting, which can affect Earth's rotation. Despite all these complex interactions and hidden forces, Earth's rotation remains remarkably stable. The planet's enormous angular momentum acts like a flywheel, smoothing out short-term variations and maintaining long-term stability. It's like a massive ship that can weather small storms without changing course. The precision with which Earth maintains its rotation is truly remarkable. The variations in the length of day, even with all these forces at work, are typically measured in milliseconds. For a planet spinning at 1,000 miles per hour at the equator, this level of stability is extraordinary. Modern technology allows us to measure these tiny variations with incredible precision. Scientists use atomic clocks, satellite measurements, and other advanced techniques to track changes in Earth's rotation with an accuracy that would have been unimaginable just a few decades ago. This research has revealed the intricate dance of forces that keep our planet spinning steadily through space. As we continue to study these hidden forces, we gain a deeper appreciation for the complexity and elegance of Earth's rotational system. Every force, every interaction, every subtle influence contributes to the overall stability that makes life on Earth possible. It's a testament to the remarkable way that complex systems can achieve stability through the interplay of multiple forces and influences. The story of Earth's balance is far from over. As we face challenges like climate change, which affects ice distribution, sea levels, and atmospheric patterns, we're seeing how human activities can influence these ancient, hidden forces. Understanding these connections helps us appreciate not just the remarkable stability of our planet, but also our responsibility to protect the delicate balance that has sustained life on Earth for billions of years. In the next part of our journey, we'll explore how Earth's rotation affects life on our planet, and how living systems have adapted to and even influenced the planet's spin. The story of Earth's balance is not just a tale of physics and geology, it's also a story of life itself, and how all living things are part of the grand dance of our spinning planet. Imagine holding a spinning bicycle wheel by its axle, feeling the strange tugging sensation as you try to tilt it. There's something almost magical about the way it resists your efforts, pushing back with an invisible force that seems to have a mind of its own. This is the essence of gyroscopic effect, and our Earth, spinning through the cosmos, is perhaps the most magnificent gyroscope ever created. Picture our planet as a massive spinning top, weighing in at nearly 6 trillion kilograms, rotating once every 24 hours. But unlike a simple toy top that wobbles and eventually falls over, Earth maintains its spin with remarkable stability. This isn't mere coincidence or luck. It's the result of fundamental physical principles that govern how rotating objects behave in space. The secret lies in something called angular momentum, a concept that sounds complex, but is actually quite beautiful in its simplicity. Think of it as the rotational equivalent of regular momentum, the tendency of moving objects to keep moving. Just as a rolling ball wants to continue rolling in a straight line, a spinning object wants to keep spinning around the same axis. Earth's enormous mass and its rotation create a tremendous amount of angular momentum, like a cosmic flywheel that resists any attempts to change its motion. When you watch a figure skater spinning with arms outstretched, then pulling them in close to spin faster, you're witnessing the conservation of angular momentum in action. The skater's total angular momentum remains constant. So when they reduce their moment of inertia by pulling in their arms, they must spin faster to compensate. Earth operates on this same principle, but on a scale so vast it's almost incomprehensible. Our planet's angular momentum is pointing in a specific direction, straight out through the North Pole and into space, toward a point near the star Polaris. This invisible arrow of rotational energy is what keeps Earth's axis stable relative to the stars. It's as if our planet is a giant compass needle, but instead of pointing toward magnetic north, it's pointing toward a fixed direction in space. The gyroscopic effect becomes even more fascinating when we consider how Earth responds to external forces. When the moon and sun try to pull on our planet's equatorial bulge, attempting to align it with their gravitational fields, Earth doesn't simply tip over. Instead, it responds like a gyroscope, with its axis slowly tracing out a circle. In space over the course of about 26,000 years, this phenomenon, called precession, is Earth's way of maintaining its spin while accommodating the gravitational tugs from its celestial neighbors. Think of it like this. If you try to push over a spinning gyroscope, it doesn't fall in the direction you push. Instead, it moves at a right angle to your push, maintaining its spin while slowly rotating around a new axis. Earth does exactly the same thing, but on a timescale that spans hundreds of human generations. The gravitational forces from the moon and sun create a torque that tries to tip our planet. But our gyroscopic Earth responds by precessing, slowly changing the direction. Its axis points in space. This precession is so gradual that ancient civilizations didn't notice it during their lifetimes. It was only through careful observations, spanning centuries, that astronomers discovered this cosmic dance. What they found was that the North Star hasn't always been the North Star. Thousands of years ago, different stars marked the northern direction, and thousands of years from now, the title will pass to yet other stars as Earth's axis continues. Its slow, majestic circle. The mathematics behind this gyroscopic behavior are elegant and precise. Earth's angular momentum vector, with a magnitude of about 7 times 10 to the 33rd power kilogram meters squared per second, creates a gyroscopic couple that resists any change in orientation. When external torques try to alter this orientation, the resulting precession occurs at a rate that depends on the strength of the applied torque and the magnitude of the angular momentum. But Earth's gyroscopic stability isn't just about the big picture of precession. It also helps maintain our planet's orientation on much shorter timescales. Without this gyroscopic rigidity, Earth might wobble chaotically like a poorly balanced top, creating wild variations in climate and seasons that would make life as we know it impossible. The gyroscopic effect acts like a cosmic stabilizer, keeping our world steady and predictable, deep within Earth's interior. An intricate ballet of angular momentum unfolds, invisible to our eyes, but crucial to our planet's stability. This dance involves multiple partners: the solid inner core, the liquid outer core, the rocky mantle, and the thin crust upon which we live. Each layer rotates at slightly different rates, creating a complex system of interacting angular momenta that keeps our world in perfect balance. The conservation of angular momentum is one of nature's most fundamental laws. As unbreakable as the conservation of energy, it states that in the absence of external torques, the total angular momentum of a system remains constant. For Earth, this means that if one part of our planet speeds up its rotation, another part must slow down by exactly the same amount. It's like a cosmic accounting system where every debit must have an equal credit. Picture Earth's inner core, a solid sphere of iron and nickel roughly the size of the moon, spinning independently within the liquid outer core. This inner core rotates slightly faster than the rest of the planet, gaining about 1 degree per year on the surface. But this isn't a runaway process. The angular momentum lost by the inner core as it spins faster must be gained somewhere else in the system. The liquid outer core, surrounding the inner core like a turbulent metal sea, plays a crucial role in this exchange. Convection currents in this molten iron flow at different speeds and directions, creating eddies and streams that transfer angular momentum between the core and the mantle above. These fluid motions are driven by heat from the inner core and cooling from the mantle, creating a dynamic system that's constantly adjusting and rebalancing. When scientists detect tiny changes in the length of Earth's day, variations of just milliseconds, they're observing this angular momentum exchange in action. Sometimes the core spins up, stealing angular momentum from the mantle and making our days slightly longer. Other times, the process reverses and the core slows down, returning angular momentum to the mantle and shortening our days. These exchanges happen on timescales ranging from years to decades, creating what scientists call the decade fluctuation in Earth's rotation. It's as if our planet has its own internal clock, running fast or slow depending on the complex dynamics, occurring thousands of kilometers beneath our feet. The changes are so small that you'd need an atomic clock to detect them, but they reveal the intricate choreography of angular momentum conservation happening within our world. The solid mantle, comprising most of Earth's bulk, serves as the primary reservoir of angular momentum. Its vast mass and steady rotation provide the stability that keeps our planet's day length remarkably consistent over long periods. When the core mantle system exchanges angular momentum, the mantle's enormous inertia means that even significant changes in the core's rotation rate produce only tiny variations in the day length. But the mantle isn't entirely passive in this dance. Convection currents in the mantle, driven by heat from the core and radioactive decay, create slow-moving circulation patterns that transport mass and angular momentum over millions of years. These currents carry hot material from the core mantle, boundary to the surface, where it cools and descends again, creating a grand circulation that influences Earth's rotation on geological timescales. The surface of our planet adds another layer of complexity to this angular momentum ballet. The atmosphere, oceans, and even the solid crust itself participate in the exchange. Strong winds can actually speed up or slow down Earth's rotation by tiny amounts, transferring angular momentum between the atmosphere and the solid Earth. The seasonal cycle of winds creates an annual variation in day length of about a millisecond. As the atmospheric circulation strengthens and weakens with the changing seasons, ocean currents, too, play their part in this cosmic dance. The massive circulation patterns in the oceans carry angular momentum around the globe, and changes in these currents can affect Earth's rotation rate. The El Niño phenomenon, for instance, alters ocean circulation patterns enough to create measurable changes in the length of the day, demonstrating how even surface processes can influence our planet's angular momentum budget. Perhaps most remarkably, earthquakes can also participate in this angular momentum exchange. When massive sections of Earth's crust suddenly shift during a major earthquake, they can redistribute mass and change the planet's moment of inertia. The 2011 earthquake and tsunami in Japan, for example, shifted enough mass toward Earth's axis to speed up the planet's rotation and shorten the day by about 1.8 microseconds. This redistribution of mass affects Earth's rotation through the same principle that makes a figure skater spin faster when they pull in their arms. When mass moves closer to the axis of rotation, the moment of inertia decreases, and conservation of angular momentum requires the rotation rate to increase. Conversely, when mass moves away from the axis, the rotation slows down. The dance of angular momentum extends even to the glacial cycles that have shaped Earth's climate over millions of years. As massive ice sheets advance and retreat, they redistribute enormous amounts of water between the polar regions and the oceans. This redistribution changes Earth's moment of inertia and creates variations in the rotation rate that persists for thousands of years during ice ages, when vast amounts of water are locked up in glaciers near the poles. Earth's mass distribution becomes more concentrated toward the axis of rotation. This reduces the moment of inertia and speeds up the planet's rotation, making days slightly shorter. When the ice melts and returns to the oceans, the mass redistribution reverses, and the rotation slows down again. These glacial effects on Earth's rotation are so significant that they can be detected in the geological record. Ancient coral reefs, which grow in daily layers, preserve evidence of changing day lengths over millions of years. By counting these growth rings, scientists can trace the history of Earth's rotation and uncover the long-term patterns of angular momentum exchange. Even as Earth spins with remarkable stability, it's not perfectly steady. Like a top that's starting to slow down, our planet wobbles slightly as it rotates, tracing out tiny circles in space with a motion so subtle that it went unnoticed for most of human history. This wobble, discovered in the late 1800s by an American astronomer named Seth Chandler, reveals another layer of complexity in Earth's balancing act. The Chandler wobble, as it came to be known, causes Earth's axis to describe a small circle about 20 feet in diameter, completing one full circuit every 433 days. To put this in perspective, imagine the North Pole wandering around a circle roughly the size of a basketball court, taking just over a year to complete each lap. It's a tiny motion on the scale of our planet, but it represents a fascinating aspect of Earth's rotational dynamics. This wobble isn't random. It's a natural consequence of Earth's shape and the way it spins. Our planet isn't a perfect sphere. It's slightly flattened at the poles and bulges at the equator due to its rotation. This oblate shape means that Earth has three different moments of inertia, one for each of the three principal axes. When a body with this asymmetrical mass distribution spins, it naturally wants to wobble, much like a slightly unbalanced wheel. The physics behind this wobble are described by what scientists call the free nutation of a rotating body. In simple terms, it's the motion that occurs when a spinning object with an asymmetrical mass distribution is left to rotate freely without any external forces. The period of this free nutation depends on the object's shape and rotation rate, and for Earth, the calculated period matches almost perfectly with the observed 433-day Chandler wobble. But here's the remarkable thing about Earth's wobble. It should have died out long ago. The energy required to maintain this motion should have been dissipated through friction and other damping mechanisms within just a few decades. The fact that the wobble persists tells us that something is continuously exciting it, adding energy to keep the motion alive. For decades, the source of this excitation remained a mystery. Scientists proposed various mechanisms: atmospheric pressure changes, earthquakes, ocean currents, even the melting and freezing of polar ice. It wasn't until sophisticated computer models were developed that researchers finally solved the puzzle. The primary driver of the Chandler wobble turns out to be fluctuations in ocean bottom pressure, caused by changes in ocean circulation patterns. As ocean currents strengthen and weaken, they create pressure variations on the seafloor that are transmitted through the solid Earth. These pressure changes redistribute mass within the planet, shifting the axis of rotation and maintaining the wobble. It's a beautifully complex system where the fluid motions of the oceans couple with the solid Earth's rotation to create a persistent, measurable effect. The atmosphere also contributes to the wobble, though to a lesser extent. Seasonal changes in atmospheric pressure, the movement of large weather systems, and even the annual cycle of snow accumulation and melting all add their small contributions to the motion. Together, these various mechanisms provide just enough energy to keep Earth's wobble alive, decade after decade. But the Chandler wobble isn't the only way Earth's axis moves. Superimposed on this 433-day cycle is an annual wobble with a period of exactly 1 year. This annual motion is much more predictable, driven by the seasonal redistribution of mass as the atmosphere and oceans respond to the changing patterns of solar heating throughout the year. During Northern Hemisphere summer, the atmosphere expands and shifts mass toward the north, causing the axis to move in one direction. 6 months later, during Northern Hemisphere winter, the mass distribution reverses, and the axis moves back. This creates a yearly cycle of polar motion that, while larger in amplitude than the Chandler wobble, is much more regular and predictable. The combination of these two wobbles, the 433D Chandler wobble and the annual cycle, creates a complex pattern of polar motion that can be tracked with extraordinary precision using modern satellite techniques. The International Earth Rotation and Reference Systems Service monitors these tiny movements continuously, providing data that helps scientists understand not just Earth's rotation, but also the dynamic processes occurring within our planet's fluid systems. These measurements have revealed that Earth's axis doesn't just wobble in predictable patterns, it also undergoes longer-term changes that reflect major shifts in the planet's mass distribution. The melting of glaciers and ice sheets, changes in groundwater storage, and even the construction of large dams can all influence the position of Earth's axis over timescales of years to decades. Recent research has shown that climate change is actually shifting Earth's axis in a new direction. As the massive loss of ice from Greenland and Antarctica redistributes water to the oceans, this ongoing change in polar motion provides yet another example of how Earth's rotation is intimately connected to all the dynamic processes occurring on and within our planet. The wobble of Earth's axis might seem like an obscure astronomical phenomenon, but it has practical implications for our modern technological society. The precise positioning systems that guide our GPS satellites, the telescopes that track asteroids and space debris, and the navigation systems that guide ships and aircraft all must account for these tiny movements of Earth's axis. In our interconnected world, even the smallest wobbles of our planet can have far-reaching effects. Understanding Earth's wobble also provides insights into the planet's interior structure. The amplitude and period of the wobble depend on the distribution of mass within Earth, particularly the properties of the core mantle boundary. By studying how the wobble changes over time, scientists can infer details about the density and elastic properties of materials deep within our planet, regions that are otherwise completely inaccessible to direct observation, invisible and intangible, yet absolutely crucial to Earth's stability. Flows a vast magnetic field that extends from deep within our planet's core to the far reaches of space. This magnetic field, generated by the churning motion of liquid iron in Earth's outer core, plays a subtle but important role in maintaining our planet's rotational balance. It's a cosmic phenomenon that demonstrates how different aspects of Earth's dynamics are interconnected in ways both profound and surprising. The story of Earth's magnetic field begins nearly 3,000 kilometers beneath our feet. In the liquid iron outer core, where temperatures rival those on the surface of the Sun, here, convection currents driven by heat from the inner core create a complex pattern of fluid motion that, combined with Earth's rotation, generates electrical currents. These currents, in turn, create magnetic fields that amplify and sustain themselves in a process scientists call the geodynamo. This magnetic field generation is intimately connected to Earth's rotation through what's known as the Coriolis effect. As the liquid iron moves within the rotating reference frame of the planet, it experiences forces that organize its motion into columns and spirals aligned with the axis of rotation. This organization is crucial for maintaining the magnetic field without Earth's spin. The convection would be chaotic and unable to sustain a coherent magnetic field. The magnetic field itself, once generated, interacts with the rotation in fascinating ways. The field lines, which emerge from the core and extend into space, carry angular momentum and can transfer it between different parts of the planet. Changes in the magnetic field, strength, or configuration can therefore influence Earth's rotation rate, creating a feedback loop between the planet's magnetism and its spin. Scientists have discovered that variations in Earth's magnetic field correlate with changes in the planet's rotation rate on timescales ranging from years to decades. When the magnetic field strengthens, it appears to extract angular momentum from the core, causing the surface rotation to speed up slightly. Conversely, when the field weakens, angular momentum is returned to the core and the surface rotation slows down. This magnetic influence on rotation operates through electromagnetic coupling between the liquid outer core and the solid inner core and mantle. The magnetic field lines threading through these regions create electromagnetic forces that can speed up or slow down different parts of the planet. It's a delicate balance, with the magnetic field acting as both a generator of rotational variations and a stabilizing influence that prevents more dramatic changes. The Earth's magnetic field also provides stability through its interaction with the solar wind, the stream of charged particles flowing from the sun. Without our magnetic field, this solar wind would gradually strip away our atmosphere, as appears to have happened on Mars. The magnetic field creates a protective bubble, the magnetosphere, that deflects most of the solar wind and maintains the atmospheric mass that contributes to Earth's moment of inertia. Even more intriguingly, the magnetic field may play a role in the long-term stability of Earth's rotation axis. Some scientists theorize that the electromagnetic forces generated by the geodynamo could provide a small but persistent torque that helps maintain the planet's axial tilt. This magnetic stabilization would work alongside the gravitational influences of the Moon and Sun to keep Earth's orientation relatively stable over geological time. The magnetic field's influence extends beyond Earth itself through its interaction with the Moon's orbit. The Moon passes through Earth's magnetic tail, the long extension of the magnetosphere that trails behind our planet, for several days each month. During these passages, electromagnetic forces act on the Moon, creating tiny perturbations in its orbit that eventually feed back to affect Earth's rotation. These magnetic effects on the Earth-Moon system are incredibly subtle, but they accumulate over millions of years to produce measurable changes in the system's dynamics. The magnetic field essentially acts as a weak but persistent coupling between Earth's rotation and the Moon's orbital motion, adding another layer of complexity to the celestial mechanics that govern our planet's stability. The geodynamo that generates Earth's magnetic field operates on multiple time scales, from rapid fluctuations lasting hours or days to long-term variations spanning millions of years. These magnetic variations are recorded in the planet's rotation through the electromagnetic coupling mechanisms, creating a complex pattern of rotational changes that reflects the deep interior dynamics of our planet. Perhaps most remarkably, the magnetic field occasionally reverses completely, with the north and south magnetic poles switching places. These magnetic reversals occur irregularly, with the last one happening about 780,000 years ago. During a reversal, the magnetic field weakens dramatically before re-establishing itself in the opposite direction. These events appear to be accompanied by subtle changes in Earth's rotation, suggesting that the magnetic field plays a more significant role in rotational dynamics than previously thought. The study of ancient magnetic reversals, preserved in the magnetization of rocks and sediments, provides a window into Earth's rotational history. By analyzing these magnetic records alongside other indicators of past rotation rates, scientists can reconstruct how Earth's spin has changed over millions of years and understand the long-term relationship between magnetism and rotation. Modern satellite missions have revolutionized our ability to monitor Earth's magnetic field and its relationship to rotation. The European Space Agency's Swarm mission, for example, uses a constellation of satellites to map the magnetic field with unprecedented precision, revealing new details about how magnetic and rotational dynamics are connected. These observations are helping scientists develop more sophisticated models of the geodynamo and its influence on Earth's rotation. The magnetic field's role in Earth's rotational stability extends even to its influence on climate and weather patterns. The field affects the penetration of cosmic rays into the atmosphere, which in turn influences cloud formation and climate. Changes in climate can redistribute mass between the atmosphere, oceans, and ice sheets, affecting Earth's moment of inertia and rotation rate. In this way, the magnetic field indirectly influences rotation through its effects on the planet's climate system. As we look toward the future, understanding the magnetic field's role in Earth's rotational stability becomes increasingly important. Climate change is already affecting the planet's mass distribution through ice melting and sea level rise, and these changes are beginning to influence Earth's rotation in measurable ways. The magnetic field's response to these changes and its feedback on rotational dynamics will be crucial factors in predicting how Earth's rotation will evolve in the coming centuries. The magnetic field thus serves as both a recorder and a moderator of Earth's rotational dynamics, creating a complex feedback system that has helped maintain our planet's stability for billions of years. It's an invisible force that connects the deepest interior of our planet to the vastness of space, demonstrating once again how Earth's various systems work together to create the stable, balanced world we call home. There's something almost magical about watching the ocean's edge, the way the water seems to breathe with a rhythm all its own. Twice each day, the sea reaches up the shore with gentle fingers, then slowly retreats, leaving behind shells and seaweed-like gifts from another world. Most of us have experienced this mesmerizing dance of the tides, but few truly understand the profound cosmic ballet that creates this daily miracle. The tides are not just water moving back and forth, they are the visible signature of invisible forces that reach across the vastness of space to touch our planet with gravitational hands. To understand how Earth keeps its balance while spinning, we must dive deep into the nature of tidal forces, for they are among the most important players in our planet's delicate equilibrium. These forces are subtle yet powerful, gentle yet relentless, and they work their magic not just on our oceans, but on the very solid Earth beneath our feet. Every moment of every day, tidal forces are sculpting our planet's rotation, adjusting its spin, and maintaining the stability that makes life possible. Imagine for a moment that you're holding a rubber ball in your hands. Now picture trying to stretch that ball by pulling on opposite sides. The side closer to you experiences a stronger pull than the side farther away. And this difference in gravitational strength creates what we call a tidal force. This is exactly what happens to our Earth as it orbits through space, surrounded by the gravitational fields of the Moon, the Sun, and even the distant planets. The Moon, our closest celestial neighbor, exerts the strongest tidal influence on Earth, even though it's much smaller than our planet. The Moon's proximity gives it tremendous power over our world. The gravitational force between any two objects depends not just on their masses, but on the distance between them, and distance plays a crucial role in a very specific way. Gravity doesn't just weaken with distance, it follows what scientists call an inverse square law, meaning that if you double the distance, the gravitational force becomes 4 times weaker. But here's where the magic of tidal forces begins to reveal itself. The moon doesn't just pull on Earth as a whole, it pulls on every part of our planet with slightly different strength. The side of Earth facing the moon experiences a stronger gravitational pull than the planet's center, while the side facing away from the moon experiences a weaker pull. This creates a stretching effect, as if the moon were gently trying to pull our planet apart with invisible hands. Picture Earth as a dancer spinning in space, with the moon as her partner, always maintaining their cosmic waltz. The moon's gravity doesn't just tug at our planet uniformly, it creates a gradient of force across Earth's diameter. The difference between the strongest pull on the near side and the weakest pull on the far side is what we call the tidal force. This force is surprisingly small compared to Earth's own gravity, but it's persistent and it never stops working. The most obvious effect of this tidal stretching is the rise and fall of our oceans. Water, being fluid, responds readily to these gravitational variations. On the side of Earth facing the moon, the stronger gravitational pull creates a bulge of water that reaches toward our celestial companion. But here's where many people get confused. There's also a bulge on the opposite side of Earth, the side facing away from the moon. This happens because the moon's gravity is pulling the solid Earth more strongly than it pulls the water on the far side, effectively leaving that water behind to create a second bulge as Earth rotates on its axis, carrying us through our daily cycle of day and night. These tidal bulges remain roughly aligned with the moon's position. This means that any point on Earth's surface passes through both bulges approximately every 24 hours and 50 minutes, the time it takes for the moon to return to the same position relative to a point on Earth's surface. This is why most coastal areas experience 2 high tides and 2 low tides each day, a rhythmic breathing of the ocean that has shaped coastal life for billions of years. But the story doesn't end with the oceans. The solid Earth itself, the rock and metal that makes up our planet's body, also responds to tidal forces. The ground beneath your feet rises and falls by about 30 centimeters twice each day, a slow, imperceptible tide in the very bedrock of our world. This solid Earth tide is much smaller than the ocean tides because rock is far less flexible than water. But it's there nonetheless, a constant reminder that our entire planet is being gently massaged by the gravitational forces of space. The atmosphere, too, participates in this cosmic dance. Air, like water, is fluid and responds to tidal forces. Atmospheric tides cause subtle changes in air pressure that can be measured with sensitive instruments. These atmospheric tides are actually caused more by the sun than by the moon, due to the way solar heating interacts with gravitational forces. But they add another layer to the complex symphony of tidal effects that shape our world. What makes tidal forces so crucial to Earth's rotational balance is their interaction with our planet's spin. The Earth rotates faster than the moon orbits around us. Our day is about 24 hours long, while the moon takes about 27 days to complete one orbit. This means that Earth's rotation is constantly trying to drag the tidal bulges ahead of the moon's position. The moon's gravity tries to keep these bulges aligned with its own position, creating a constant tug-of-war between Earth's rotation and the Moon's gravitational influence. This tug-of-war manifests as friction, not the kind of friction you might feel between two solid objects, but a more subtle form of energy dissipation. The tidal bulges, especially in the oceans, create currents and movements that ultimately convert some of Earth's rotational energy into heat. It's as if the Moon is acting as a gentle but persistent brake on Earth's rotation, gradually slowing our planet's spin over geological timescales. The fascinating thing about this tidal braking effect is that it's not uniform across Earth's surface. The shallow seas and continental shelves, where tidal currents encounter the ocean floor, create the most friction. Places like the Bering Sea, the English Channel, and the seas around Indonesia are particularly effective at dissipating tidal energy. These regions act like the brake pads in this cosmic braking system, gradually stealing energy from Earth's rotation and converting it to heat. But perhaps the most remarkable aspect of tidal forces is how they demonstrate the interconnectedness of our cosmic neighborhood. The Moon's gravity doesn't just affect our tides, it influences the very stability of our planet's rotation. Through tidal forces, the Moon acts as a kind of cosmic stabilizer, helping to maintain Earth's rotational balance in ways that are crucial for life as we know it. In the quiet hours before dawn, when the world seems to hold its breath, you can sometimes see the Moon hanging in the western sky like a gentle guardian watching over our sleeping planet. There's something profoundly comforting about the Moon's presence, a sense that all is well in the cosmic order. And indeed, the Moon's influence on Earth goes far beyond the romantic poetry it has inspired throughout human history. Our lunar companion plays a crucial role in maintaining the delicate balance that keeps our planet spinning steadily on its axis, creating the stable conditions that have allowed life to flourish for billions of years. The relationship between Earth and Moon is one of the most beautiful examples of cosmic partnership in our solar system, born from the same cataclysmic event that shaped our planet, most likely a Mars-sized object colliding with the early Earth. The Moon has been our constant companion for over 4 billion years. During this vast span of time, the Moon has evolved from a close, rapidly orbiting companion to the more distant, stately presence we see today. But throughout this entire journey, the Moon has been quietly working to maintain Earth's rotational stability. One of the most profound ways the Moon influences Earth's balance is through its effect on our planet's obliquity, the angle at which Earth's axis tilts relative to its orbital plane around the Sun. Currently, Earth's axis tilts at about 23.5 degrees, giving us our seasons as different parts of the planet receive varying amounts of solar radiation throughout the year. This tilt might seem arbitrary, but it's actually maintained within a relatively narrow range by the Moon's gravitational influence. Without the Moon's stabilizing presence, Earth's obliquity would be free to wander chaotically over geological timescales. Computer simulations show that a moonless Earth would experience dramatic swings in axial tilt, potentially ranging from nearly upright to completely on its side. Such extreme variations would create climatic chaos, with ice ages and scorching periods alternating unpredictably. The polar regions might sometimes point directly at the Sun, while the equator could be plunged into permanent winter. Such conditions would make the evolution of complex life extremely difficult, if not impossible. The Moon's stabilizing effect on Earth's obliquity works through a phenomenon called torque, just as the Moon creates tidal bulges in Earth's oceans. It also exerts gravitational forces on the slight equatorial bulge that Earth maintains due to its rotation. Our planet is not a perfect sphere, it's slightly flattened at the poles and bulged at the equator, like a ball that's been gently squeezed. From top and bottom, this equatorial bulge provides the moon with something to grab onto, gravitationally speaking, when external forces try to change Earth's axial tilt. The moon's gravity acting on the equatorial bulge creates a restoring torque that resists these changes. It's similar to how a gyroscope resists being tilted from its spinning axis. The moon essentially acts as an external gyroscopic stabilizer, using its gravitational influence to maintain Earth's orientation in space. This stabilizing effect is so strong that it keeps Earth's obliquity variations within about 1.3 degrees. Over periods of 41,000 years, remarkably small range considering the chaotic possibilities. The moon's influence on Earth's rotational balance extends beyond just stabilizing our axial tilt. The gravitational interaction between Earth and Moon also affects the detailed motions of our planet's axis, creating subtle but important variations in Earth's orientation. These variations include precessional slow wobble of Earth's axis. That takes about 26,000 years to complete one cycle, and nutation, much smaller wobbles that occur over shorter time periods. Precession is perhaps the most famous of these axial motions, as Earth spins like a top. The combined gravitational influences of the Moon and Sun cause our planet's axis to slowly trace out a circle in space. This precession is why the North Star changes over long periods of time. Currently, Polaris serves as our pole star, but 5,000 years ago, the star Thuban held this position. And 12,000 years from now, the bright star Vega will become our northern guide. The moon's contribution to Earth's precession is substantial, accounting for about 2/3 of the total precessional motion. This lunar influence creates what astronomers call the lunar-solar precession, distinguishing it from the much smaller effects caused by the gravitational pull of the planets. The moon's role in precession is another example of how our satellite helps maintain the orderly cycles that characterize Earth's motion through space, nutation. The smaller scale wobbles in Earth's axis is also primarily caused by the moon's gravitational influence. These wobbles have periods ranging from about 18.6 years down to just a few days, and they're caused by the complex way the moon's orbit interacts with Earth's rotation. The moon's orbit is not a perfect circle, and its plane is tilted relative to Earth's equator as the moon moves through its orbital cycle. These geometric complexities create varying gravitational forces that cause Earth's axis to nod and wobble in intricate patterns. While these nutational motions are small, typically measured in fractions of an arcsecond, they represent another way the moon helps maintain Earth's rotational balance. By causing regular, predictable variations in Earth's orientation, the moon prevents the accumulation of larger, potentially destabilizing perturbations. It's as if the moon is constantly fine-tuning Earth's spin, making tiny adjustments that keep our planet's rotation smooth and stable. The moon's influence on Earth's rotation is not static, but evolves over time due to tidal acceleration. As we discussed earlier, the friction created by tidal forces gradually slows Earth's rotation, while simultaneously causing the moon to spiral outward to a higher orbit. This process is incredibly slow by human standards. Earth's day is lengthening by about 1.7 milliseconds per century, and the moon is receding at about 3.8 centimeters per year. But over geological timescales, these changes are profound in the early history of the Earth-Moon system. When the moon was much closer to Earth, our planet rotated much faster. the moon's tidal influence was stronger, and the length of Earth's day was correspondingly shorter. Computer models suggest that when the moon first formed, Earth may have had a day length of only 5 to 6 hours. The moon was also much larger in Earth's sky, appearing perhaps 10 to 20 times bigger than it does today. As the moon gradually receded due to tidal acceleration, Earth's rotation slowed, and the length of our day increased. This process has been going on for billions of years and will continue into the distant future. Eventually, if the sun doesn't evolve into a red giant first, Earth and moon will become tidally locked to each other, with Earth always showing the same face to the moon, just as the moon currently shows the same face to Earth. At that point, Earth's day and the moon's orbital period will both be about 47 of our current days long. The moon's governance of Earth's rotation extends to more subtle effects as well. The lunar gravitational field interacts with Earth's own gravity field in complex ways, creating what scientists call gravitational coupling. This coupling affects how energy and angular momentum are transferred between different parts of Earth's system: the solid Earth, the oceans, and the atmosphere. The moon's influence helps coordinate these energy transfers, contributing to the overall stability of Earth's rotation. Recent research has revealed that the moon's influence on Earth's rotation may even extend to the motions of our planet's core. The liquid iron core that generates Earth's magnetic field is subject to gravitational forces from the moon, and these forces may influence the complex patterns of fluid motion deep within our planet. While this research is still in its early stages, it suggests that the moon's role in Earth's rotational balance may be even more comprehensive than previously thought. The moon's gentle governance of Earth's rotation is a testament to the intricate connections that exist throughout our solar system. What appears to be a simple, solitary satellite orbiting our planet is actually a crucial partner in maintaining the conditions that make Earth a stable, habitable world. The moon's gravitational influence reaches into every aspect of our planet's rotation, from the grand cycles of precession to the subtle wobbles of nutation, from the stabilization of our axial tilt to the gradual evolution of our day length. There's a profound irony in the relationship between Earth and its moon that few people truly appreciate. While we often think of our lunar companion as a static, unchanging presence in the night sky, the moon is actually locked in a slow-motion dance with Earth that has been subtly transforming both bodies for billions of years. The moon is not just a passive observer of Earth's rotation, it's an active participant in a cosmic brake system that has been gradually slowing our planet's spin since the very beginning of the Earth-Moon partnership. This cosmic braking system operates through a mechanism that's both elegant and relentless. Every time the ocean tides rise and fall, every time the solid Earth flexes under the moon's gravitational influence, a tiny amount of energy is being extracted from Earth's rotation and dissipated as heat. The process is so gradual that it's imperceptible on human timescales, but over geological time, it has profoundly shaped the evolution of our planet and its satellite. To understand how this cosmic brake system works, we need to think about the timing of the tides. If Earth were not rotating, the tidal bulges in our oceans would remain perfectly aligned with the moon's position. The moon would pull on these bulges symmetrically, creating no net torque on Earth's rotation. But Earth does rotate, and it rotates faster than the moon orbits around us. This means that Earth's rotation is constantly trying to drag the tidal bulges ahead of the moon's position. Imagine trying to pull a heavy object across a rough surface. The friction between the object and the surface resists your efforts, creating a force that opposes the motion. In the Earth-Moon system, the tidal bulges play the role of the heavy object, and the various forms of friction from ocean currents flowing over the seabed to the internal friction within the solid Earth act as the rough surface. The Moon's gravity provides the pulling force, but the friction prevents the bulges from staying perfectly aligned with the Moon. This misalignment is crucial to the braking effect, because the tidal bulges are slightly ahead of the Moon's position. The Moon's gravitational pull on these bulges creates a torque that opposes Earth's rotation. It's as if the Moon is constantly reaching out with gravitational hands, trying to grab on to the tidal bulges and slow them down. The result is a gradual transfer of angular momentum from Earth's rotation to the Moon's orbital motion. The beauty of this system lies in its conservation of energy and angular momentum. The energy that's extracted from Earth's rotation doesn't simply disappear. It gets converted into heat through various friction processes, and it also gets transferred to the Moon's orbital motion. As Earth's rotation slows down, the Moon's orbital energy increases, causing our satellite to spiral outward into a higher orbit. This is why the Moon is gradually moving away from Earth at about 3.8 centimeters per year roughly, the rate at which your fingernails grow. The cosmic brake system operates most efficiently in Earth's shallow seas and continental shelves, where tidal currents encounter the ocean floor. These regions act like the brake pads in this celestial braking system, creating turbulence and friction that effectively dissipate tidal energy. The Bering Sea, the English Channel, the Irish Sea, and the seas around Indonesia are particularly effective at this energy dissipation, contributing disproportionately to the overall braking effect. The strength of the cosmic brake system depends on several factors, including the configuration of Earth's continents and oceans, the depth of the seas, and the roughness of the ocean floor. Throughout Earth's history, changes in these factors have varied the efficiency of tidal energy dissipation. During periods when continents were arranged differently or when sea levels were higher or lower, the braking effect was correspondingly stronger or weaker. For example, during the Paleozoic era, when much of Earth's land was concentrated in a single supercontinent called Pangaea, the tidal energy dissipation was likely quite different from today. The arrangement of continents and oceans affects the resonance patterns of tidal waves, and different configurations can either amplify or dampen the tidal currents that drive the energy dissipation process. The cosmic brake system has had profound effects on Earth's climate and geology over geological timescales. The gradual slowing of Earth's rotation has increased the length of our day, from perhaps 5 to 6 hours when the Moon first formed to our current 24-hour day. This increase in day length has had subtle but important effects on atmospheric circulation, patterns, ocean currents, and the distribution of solar heating across Earth's surface. Shorter days in Earth's early history would have created different weather patterns and ocean currents. The Coriolis effect, which deflects moving objects due to Earth's rotation, would have been stronger when Earth was spinning faster. This would have created more intense atmospheric and oceanic circulation patterns, potentially affecting everything from storm systems to the distribution of heat around the planet. The cosmic brake system also affects the stability of Earth's rotation. In more subtle ways, the tidal forces that slow Earth's rotation also interact with variations in the planet's moment of inertia caused by internal processes. When mass moves within Earth, whether through plate tectonics, volcanic activity, or changes in ice distribution, it can alter the planet's moment of inertia, which in turn affects the rotation rate. The moon's tidal influence helps to smooth out these variations, providing a stabilizing influence on Earth's rotational dynamics. One of the most fascinating aspects of the cosmic brake system is its self-regulating nature. As the moon moves farther away from Earth, the tidal forces that drive the braking effect become weaker. This means that the rate of energy dissipation gradually decreases over time, and the moon's outward spiral correspondingly slows down. Eventually, the system will reach a state of equilibrium where Earth and Moon become tidally locked to each other, with both bodies showing the same face to each other at all times. This tidal locking represents the ultimate endpoint of the cosmic brake system. When it occurs, Earth's rotation period and the Moon's orbital period will be equal, eliminating the relative motion that drives the tidal energy dissipation. At that point, the braking effect will essentially stop, and the Earth system will have reached a state of rotational equilibrium based on current rates of change. This tidal locking is expected to occur in about 50 billion years, long after the Sun has evolved into a red giant and made Earth uninhabitable. The cosmic brake system operating between Earth and Moon is not unique in the solar system. Similar tidal interactions occur between many other planetary bodies and their satellites. The moons of the giant planets, Jupiter, Saturn, Uranus, and Neptune are all tidally locked to their parent planets, showing that tidal braking is a common outcome of these gravitational interactions. Even some binary asteroid systems show evidence of tidal locking, demonstrating that this cosmic brake system operates across a wide range of scales. The study of tidal braking in the Earth-Moon system provides valuable insights into the evolution of other planetary systems as well. Astronomers have discovered thousands of exoplanets orbiting other stars, and many of these planets likely experience tidal forces from their parent stars. Understanding how tidal braking affects planetary rotation helps us predict the conditions on these distant worlds and assess their potential habitability. The cosmic brake system also has practical implications for life on Earth. The gradual slowing of Earth's rotation affects the accuracy of our timekeeping systems, requiring occasional adjustments to keep our clocks synchronized with Earth's actual rotation. The insertion of leap seconds into our atomic time standards is a direct consequence of the cosmic brake system. A reminder that even our most precise timekeeping must accommodate the ancient dance between Earth and Moon. There's something deeply comforting about the predictable cycle of seasons that marks the passage of time on Earth. Spring arrives with its gentle warming and budding life. Summer brings long days and abundant growth. Autumn paints the world in warm colors before winter's quiet rest. This seasonal rhythm has been the backdrop for all of life's evolution on our planet, providing the stable, predictable climate variations that have allowed complex ecosystems to develop and thrive. But few people realize that this seemingly simple cycle of seasons depends on one of the most remarkable stabilizing influences in our solar system: the Moon's role as the guardian of Earth's axial tilt. The seasons exist because Earth's axis of rotation is tilted at an angle of about 23.5 degrees relative to the plane of our orbit around the Sun. This tilt, known as obliquity, causes different parts of Earth to receive varying amounts of solar radiation throughout the year. When the northern hemisphere is tilted toward the Sun, it experiences summer, while the southern hemisphere experiences winter. 6 months later, the situation reverses, creating the opposite seasonal pattern in each hemisphere. This 23.5-degree tilt might seem like a fixed property of our planet, as unchanging as the mountains or the seas. But in reality, Earth's obliquity is constantly being influenced by gravitational forces from throughout the solar system. The Sun, the Moon, and even the planets all exert gravitational torques on Earth that could, in principle, cause dramatic changes in our planet's axial tilt. Without some stabilizing influence, Earth's obliquity could wander chaotically over geological timescales, potentially swinging from nearly 0 degrees to as much as 85 degrees. Imagine what such obliquity variations would mean for Earth's climate. If our planet's axis were nearly upright, with an obliquity close to 0, there would be no seasons at all. The poles would remain in permanent twilight, while the equator would experience the same amount of solar radiation year-round. Conversely, if Earth's axis were tilted at an extreme angle, the poles would alternately point directly at the Sun, creating scorching summers at the polar regions, while the equator experienced freezing winters. Such extreme obliquity variations would create climate chaos that would make the evolution of complex life extremely difficult. The temperature variations would be so extreme that ice ages and greenhouse periods would alternate in unpredictable ways. Ocean currents would be disrupted, weather patterns would be chaotic, and the stable climate conditions that life depends on would be impossible to maintain. Fortunately, Earth has a guardian that prevents such climate catastrophes: our Moon. The Moon's gravitational influence on Earth's equatorial bulge creates a stabilizing torque that resists changes in our planet's obliquity. This stabilizing effect is so strong that it keeps Earth's axial tilt within a narrow range of about 1.3 degrees over periods of 41,000 years. Without the Moon's influence, computer models suggest that Earth's obliquity could vary by as much as 60 degrees or more over similar time periods. The Moon's role as the guardian of seasons works through a mechanism that's both elegant and powerful. Earth is not a perfect sphere. It's slightly flattened at the poles and bulged at the equator due to its rotation. This equatorial bulge provides the Moon with a gravitational handle that it can use to influence Earth's orientation in space. When external forces try to change Earth's axial tilt, the Moon's gravity acting on the equatorial bulge creates a restoring torque that opposes these changes. This stabilizing mechanism is similar to how a gyroscope maintains its orientation. A spinning gyroscope resists being tilted from its axis of rotation, and the faster it spins, the more stable it becomes. In the Earth-Moon system, the Moon acts like an external gyroscopic stabilizer, using its gravitational influence to maintain Earth's axial orientation. The Moon's mass and its distance from Earth are perfectly balanced to provide just the right amount of stabilizing influence. The guardian effect of the Moon is not absolute. It doesn't prevent all changes in Earth's obliquity. Instead, it constrains these changes to a narrow range and ensures that they occur in predictable, periodic cycles. Earth's obliquity currently varies between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. This variation is one of the Milankovitch cycles that influence Earth's long-term climate patterns and ice age cycles. These small variations in obliquity have been crucial to Earth's climate history. They interact with other orbital cycles, changes in the shape of Earth's orbit, and the precession of the equinoxes to create the complex patterns of ice ages and warm periods that have characterized Earth's climate over the past few million years. The Moon's role in maintaining the regularity of these cycles has been essential to the relatively stable climate conditions that have allowed human civilization to develop. The Moon's guardian influence extends beyond just maintaining Earth's current obliquity. Throughout Earth's history, the Moon has helped our planet maintain a stable axial tilt, even as the Moon itself has been gradually moving away from Earth. As the moon's distance has increased over geological time, its stabilizing influence has slowly weakened, but it has remained strong enough to prevent chaotic obliquity variations. Computer simulations of Earth's obliquity evolution show that the moon's influence has been crucial throughout Earth's history. Even when the moon was closer to Earth and its tidal forces were stronger, the stabilizing effect on obliquity was maintained. This suggests that the moon has been acting as the guardian of Earth's seasons for billions of years, helping to maintain the stable climate conditions that allowed life to evolve and diversify. The importance of the moon's guardian role becomes even more apparent when we compare Earth to other planets in our solar system. Mars, for example, has two small moons, Phobos and Deimos, but they're far too small to provide any significant stabilizing influence on the planet's obliquity. As a result, Mars experiences chaotic obliquity variations that range from about 15 degrees to as much as 60 degrees over timescales of millions of years. These obliquity variations have had profound effects on Mars's climate history. When obliquity is low, the polar regions receive little solar radiation and accumulate thick ice caps. When the obliquity is high, the poles receive intense solar radiation, causing the ice caps to sublimate and create thick atmospheres. This chaotic climate history may help explain why Mars appears to have lost much of its original atmosphere and water, making it the cold, dry planet we see today. Venus, on the other hand, has no moon at all, and its obliquity is extremely unusual. The planet is nearly upside down, with an obliquity of about 177 degrees. This means that Venus rotates backward relative to most other planets, and its seasons, if it had any, would be completely reversed. The lack of a large moon may have allowed Venus's obliquity to evolve into this extreme state, though the planet's incredibly thick atmosphere and slow rotation makes seasonal effects negligible. The outer planets provide additional examples of how moons can influence obliquity. Jupiter's obliquity is very small, only about 3 degrees, which may be partly due to the stabilizing influence of its large moons. Saturn's obliquity is much larger, about 27 degrees, but its moon system is also more complex, with multiple large moons that may have different effects on the planet's axial stability. The moon's role as the guardian of seasons has profound implications for the possibility of life on other worlds. As astronomers discover more exoplanets orbiting other stars, they're beginning to realize that the presence of a large moon may be crucial for maintaining the stable climate conditions that life requires. Planets without large moons may experience chaotic obliquity variations that prevent the evolution of complex life. This realization has led to the development of the rare Earth hypothesis, which suggests that Earth-like planets with stable, life-supporting climates may be much rarer in the universe than previously thought. The moon's guardian role in maintaining Earth's obliquity stability may be one of the key factors that makes our planet so uniquely suited for life. The moon's influence on Earth's obliquity also interacts with other factors that affect our planet's climate. The distribution of continents and oceans, the composition of the atmosphere, and the brightness of the sun all play roles in determining Earth's climate. The moon's stabilizing influence helps ensure that these other factors can work together to maintain habitable conditions rather than being disrupted by chaotic obliquity variations. As we look toward the future, the moon will continue to serve as the guardian of Earth's seasons, though its influence will gradually weaken as our satellite continues to move away from Earth. The rate of this weakening is extremely slow, It will take billions of years for the Moon to move far enough away to significantly reduce its stabilizing influence. By that time, the Sun will have evolved into a red giant star, making Earth uninhabitable. Regardless of obliquity variations, the Moon's role as the guardian of seasons is perhaps one of the most profound examples of how interconnected our solar system truly is. What appears to be a simple, static satellite hanging in our night sky is actually a dynamic participant in maintaining the conditions that make life on Earth possible. The Moon's gravitational influence reaches across the vacuum of space to gently guide Earth's axial orientation, ensuring that the seasons continue their ancient cycle and that the climate remains stable enough for life to thrive. In the vast concert hall of space, Earth dances to a symphony of gravitational harmonies that extends far beyond the dominant melody played by our Moon. While the Moon's influence is certainly the most prominent in Earth's rotational balance, our planet also responds to the subtle gravitational notes played by the Sun, the planets, and even distant stars. These multiple gravitational influences create a complex, ever-changing symphony that shapes Earth's motion in space and contributes to the remarkable stability of our world. The Sun, our nearest star, and the source of virtually all energy on Earth, plays a crucial role in this gravitational symphony. While the Sun's gravitational influence on Earth's rotation is about half as strong as the Moon's, it still contributes significantly to our planet's rotational dynamics. The Sun's gravitational pull on Earth's equatorial bulge creates tidal forces that work alongside the Moon's influence to shape our planet's precessional motion and to maintain the stability of our axial orientation. The Sun's contribution to Earth's precession is particularly important, as Earth's axis slowly wobbles through its 26,000-year cycle. About 1/3 of this motion is due to the Sun's gravitational influence. This solar contribution is more constant than the Moon's influence because the Sun's distance from Earth varies much less than the Moon's distance. The Sun's steady gravitational pull helps to smooth out the variations in precessional motion that would otherwise be caused by the Moon's elliptical orbit. The interplay between solar and lunar gravitational influences creates what astronomers call the lunar-solar precession, a complex pattern of axial motion that reflects the combined effects of both celestial bodies. This precession is not uniform, but varies in rate and direction as the relative positions of Earth, Moon, and Sun change throughout their orbital cycles. The result is a rich, intricate pattern of motion that demonstrates the complexity of gravitational interactions in our solar system beyond the Sun and Moon. The planets of our solar system also contribute their own gravitational voices to the symphony. Jupiter, the largest planet, has a particularly significant influence despite its great distance from Earth. Jupiter's massive gravity field creates small but measurable perturbations in Earth's orbit, which in turn affect our planet's rotational dynamics. These planetary influences are much smaller than those of the Sun and Moon, but they add important harmonics to the overall gravitational symphony. The gravitational influence of the planets creates what astronomers call planetary precession, a very slow additional wobble in Earth's axis that occurs over much longer timescales than the primary lunar-solar precession. This planetary precession has a period of about 70,000 years and is caused by the combined gravitational effects of all the planets in our solar system. While this effect is tiny compared to the lunar-solar precession, it represents another layer of complexity in Earth's rotational motion. Venus, our closest planetary neighbor, contributes to this planetary precession despite being much smaller than Jupiter. Venus's proximity to Earth during its closest approaches creates gravitational perturbations that are detectable with precise astronomical measurements. These perturbations are part of the intricate gravitational dance that all the planets perform as they orbit the Sun, each influencing the others in subtle but measurable ways. Mars, with its elliptical orbit and varying distance from Earth, creates periodic gravitational influences that wax and wane as the two planets move through their respective orbits. When Mars is at its closest approach to Earth, its gravitational influence is strongest, creating small variations in Earth's orbital and rotational motion. These variations are incorporated into the precise models that astronomers use to predict Earth's orientation in space. The outer planets, Saturn, Uranus, and Neptune, are so distant that their individual gravitational influences on Earth are extremely small. However, when their effects are combined and considered over very long timescales, they contribute to the slow, long-term variations in Earth's orbital and rotational motion. These outer planet influences are part of the reason why Earth's motion in space exhibits such complex, multi-periodic behavior. One of the most fascinating aspects of this gravitational symphony is how all these confluences work together to create resonances and harmonics in Earth's motion. Just as musical instruments can create beautiful harmonies when their vibrations interact, the gravitational influences of different celestial bodies can create resonant patterns in Earth's rotational and orbital motion. These resonances help to stabilize Earth's motion over long timescales, preventing chaotic variations that could disrupt our planet's climate. The concept of gravitational resonance is beautifully illustrated by the way different periodic influences in Earth's motion interact with each other. For example, the 26,000-year precession cycle interacts with the 41,000-year obliquity cycle and the 100,000-year eccentricity cycle to create the complex patterns of ice ages and warm periods that have characterized Earth's climate over the past few million years. These interactions demonstrate how the gravitational symphony creates stable, predictable patterns in Earth's long-term climate evolution. The gravitational symphony also includes contributions from sources beyond our solar system. The gravitational field of our galaxy, the Milky Way, creates extremely subtle influences on Earth's motion. While these galactic influences are far too small to affect Earth's rotation directly, they contribute to the long-term evolution of our solar system's orbit around the galactic center, over timescales of millions of years. These galactic influences can affect the gravitational environment that Earth experiences. Recent research has also revealed that the gravitational influence of nearby stars can have subtle effects on the outer regions of our solar system. While these effects don't directly influence Earth's rotation, they can affect the orbits of comets and asteroids in the outer solar system, potentially influencing the frequency of impacts on Earth over very long timescales. These distant gravitational influences represent the faintest notes in the gravitational symphony that governs Earth's motion. The study of this gravitational symphony has practical applications beyond pure scientific interest. Understanding the complex gravitational influences on Earth's motion is crucial for accurate navigation and timekeeping. The Global Positioning System, GPS, and other satellite navigation systems must account for the various gravitational influences that affect Earth's rotation and orbital motion. Even tiny errors in these calculations can accumulate over time, leading to significant navigational errors. The gravitational symphony also affects our understanding of Earth's interior structure. The way Earth responds to various gravitational influences depends on the distribution of mass within our planet. By carefully studying how Earth's rotation varies in response to different gravitational forces, scientists can learn about the structure of Earth's core, mantle, and crust. This field of study, called geodesy, uses the gravitational symphony as a tool for exploring Earth's interior. Climate scientists also rely on understanding the gravitational symphony to predict long-term climate changes. The various orbital and rotational cycles that result from gravitational influences are key components of climate models that extend thousands or millions of years into the future. These models help scientists understand how Earth's climate has evolved in the past, and how it might change in the future due to both natural and human influences. The gravitational symphony that governs Earth's motion is a testament to the interconnectedness of our universe. Every object in space, from the smallest asteroid to the largest galaxy, contributes its own gravitational voice to the cosmic symphony. Earth's remarkable stability and habitability result from the way all these gravitational influences work together to create predictable, stable patterns of motion that have persisted for billions of years. As we continue to explore the universe and discover new planets orbiting other stars, understanding the gravitational symphony of our own solar system becomes increasingly important. The stability that Earth enjoys may be relatively rare in the universe, dependent on the particular arrangement of our solar system and the specific gravitational influences that govern our planet's motion. The Moon's dominant role in this symphony, combined with the Sun's steady influence and the planet's subtle harmonies, may represent a unique combination of circumstances that makes Earth particularly well suited for life. The gravitational symphony will continue to play for billions of years to come, gradually evolving as the solar system ages and the various celestial bodies change their relationships with each other. The Moon will continue to move away from Earth, gradually weakening its influence on our planet's rotation. The Sun will slowly brighten and eventually evolve into a red giant. The planets will continue their orbital dances, creating new patterns of gravitational influence over cosmic timescales. Through it all, Earth will continue to respond to this ever-changing symphony, maintaining the delicate balance that makes our world a haven for life in the vast cosmos, deep beneath our feet. Far below the solid ground we walk upon lies a world of incredible heat and motion that most of us never think about. Yet this hidden realm, nestled thousands of miles below the surface, plays one of the most crucial roles in keeping our planet balanced as it spins through space. It's a place where temperatures soar higher than the surface of the Sun, where metals flow like rivers, and where the very forces that protect all life on Earth are born. Imagine, if you will, a sphere of molten iron and nickel, roughly the size of the planet Mars, suspended in the center of our Earth. This is our planet's outer core, a churning sea of liquid metal that never rests, never sleeps, and never stops its eternal dance. The temperature here reaches nearly 5,000 degrees Celsius, hot enough to melt virtually any material we know. Yet the immense pressure keeps this metallic ocean in a state of constant fluid motion. This liquid metal ocean doesn't just sit there, peacefully. Instead, it flows and swirls in complex patterns, driven by the heat rising from the even hotter, solid inner core below and the cooler mantle above. These currents of molten metal create what scientists call convection patterns, much like the way hot water moves in a pot on your stove, but infinitely more complex and operating on a scale that defies imagination. As our planet spins on its axis, completing one full rotation every 24 hours, this liquid metal core doesn't just passively go along for the ride. The spinning motion of Earth, combined with the flowing currents of molten metal, creates something truly remarkable. A natural dynamo that generates the magnetic field surrounding our planet. This process, known as the geodynamo, is one of the most elegant examples of how Earth's rotation and internal structure work together to maintain the delicate balance that makes life possible. The magnetic field generated by this deep Earth dynamo extends far beyond our atmosphere, creating an invisible shield that protects us from the constant stream of charged particles flowing from the sun. This solar wind, as it's called, would otherwise strip away our atmosphere and make our planet as barren as Mars. But our magnetic field deflects these particles, guiding them around our planet and keeping our precious atmosphere intact. Yet the story of Earth's magnetic field is far more intricate than simple protection. This invisible force field is intimately connected to our planet's rotation and plays a subtle but important role in maintaining the stability of that rotation. The magnetic field lines that spiral out from our planet's core create a complex three-dimensional structure that extends thousands of miles into space, forming what scientists call the magnetosphere. Within this magnetosphere, the interaction between our planet's magnetic field and the solar wind creates a delicate balance of forces. When the solar wind is strong, our magnetosphere compresses, like a balloon being squeezed. When the solar wind is weak, it expands. These constant changes in the shape and strength of our magnetic field create tiny but measurable effects on Earth's rotation. Like a dancer adjusting their balance by extending or pulling in their arms, the generation of our magnetic field also depends on the precise balance of temperatures and pressures deep within our planet. If Earth was spinning much faster or much slower, the convection patterns in the liquid outer core would change dramatically, potentially weakening or even eliminating our magnetic field entirely. This is another example of how Earth's rotational speed exists in a delicate equilibrium with the other forces that shape our planet. But the story doesn't end with the liquid outer core. At the very center of our planet lies the inner core, a solid sphere of iron and nickel about the size of the moon. This inner core is even hotter than the outer core, reaching temperatures of over 6,000 degrees Celsius, but the tremendous pressure at Earth's center keeps it solid. And here's where things get truly fascinating. This inner core doesn't rotate at exactly the same speed as the rest of our planet. Recent scientific discoveries have revealed that Earth's inner core rotates slightly faster than the surface, completing an extra rotation about every 400 years. This phenomenon, called superrotation, was only discovered in the 1990s and is still not fully understood. Some scientists believe this differential rotation is driven by the magnetic field generated in the outer core, while others think it might be caused by gravitational forces from the moon and sun. Even more intriguingly, some research suggests that the inner core's rotation might not be constant. There's evidence that it sometimes speeds up, sometimes slows down, and might even occasionally reverse direction. These changes in the inner core's rotation create tiny variations in Earth's magnetic field, which in turn can influence the length of our days by microseconds. It's a reminder that even the most solid, unchanging parts of our planet are constantly in motion, constantly adjusting to maintain the delicate balance that keeps Earth spinning steadily. The interaction between the inner core, outer core, and mantle creates what scientists call angular momentum exchange. Angular momentum, as we've learned, is the tendency of spinning objects to keep spinning. When the inner core spins faster than the rest of the planet, it's like a gyroscope within a gyroscope, adding stability to Earth's overall rotation. When it slows down, that stability decreases slightly. These changes are incredibly small. We're talking about variations, measured in milliseconds per century. But they demonstrate the intricate web of forces that work together to keep our planet balanced. The solid inner core, liquid outer core, rocky mantle, and thin crust all interact through gravitational forces, magnetic fields, and the conservation of angular momentum to maintain Earth's steady rotation. The mantle, that thick layer of hot rock between the core and crust, also plays its part in this cosmic dance. Although it's solid, the mantle behaves like a very thick liquid over geological timescales, flowing and convecting in patterns that take millions of years to complete. These slow-motion currents in the mantle are driven by heat from the core and create the tectonic forces that move continents, build mountains, and trigger earthquakes. When large earthquakes occur, they can actually change the distribution of mass within Earth's crust and mantle, affecting our planet's moment of inertia, essentially how the mass is distributed around the axis of rotation. Remember the ice skater pulling in their arms to spin faster. When an earthquake moves large amounts of rock, it can have a similar effect on Earth's rotation. Though the changes are incredibly tiny, the Great 2004 earthquake and tsunami in the Indian Ocean, one of the most powerful earthquakes ever recorded, actually shortened Earth's day by 2.68 microseconds. The earthquake shifted so much mass toward Earth's axis of rotation that our planet began spinning just a tiny bit faster. Similarly, the 2011 earthquake and tsunami in Japan shortened the day by 1.8 microseconds. These changes are far too small for us to notice in our daily lives, but they demonstrate how even the solid parts of our planet are constantly adjusting to maintain rotational balance. The process works in reverse too. When ice sheets grow during ice ages, they redistribute water from the oceans to the polar regions, moving mass closer to Earth's axis of rotation and causing the planet to spin faster. When the ice melts, the water returns to the oceans, moving mass away from the axis and slowing the rotation slightly. It's another example of how Earth's various systems work together to maintain balance over long periods of time. Even the seasonal changes we experience affect Earth's rotation in measurable ways. During Northern Hemisphere winter, more snow and ice accumulate at high latitudes, moving mass closer to the axis of rotation and slightly speeding up Earth's spin. During summer, this ice melts and the mass moves away from the axis, slowing the rotation. These seasonal variations in the length of day are regular and predictable. Measured in milliseconds, the atmosphere itself participates in this delicate balance of forces. Our planet's atmosphere is held in place by gravity, but it's also set in motion by Earth's rotation. As our planet spins, the atmosphere is dragged along, creating the complex patterns of wind and weather that we experience. But the atmosphere doesn't just passively follow Earth's rotation, it can also influence it. Strong wind patterns, like the jet streams that circle the planet at high altitudes, carry angular momentum. When these winds speed up or slow down, they can transfer some of that angular momentum to or from the solid Earth, causing tiny changes in the planet's rotation rate. It's like a dancer extending or pulling in their arms. The total angular momentum stays the same, but it gets redistributed between different parts of the system. The most dramatic example of this atmospheric influence occurs during El Niño and La Niña events, when changes in ocean temperature patterns alter wind patterns around the globe. These changes can affect the length of Earth's day by up to a millisecond, demonstrating how the fluid parts of our planet, the atmosphere and oceans, are intimately connected to the solid Earth's rotation, high above our heads, extending thousands of miles into space, lies an invisible protective shell that most of us never think about, but that plays a crucial role in keeping our planet balanced and habitable. This is Earth's magnetosphere, the region of space dominated by our planet's magnetic field. And it's one of the most important yet least understood aspects of how Earth maintains its stability while spinning through the cosmos. To understand how this invisible shield contributes to Earth's balance, we need to imagine ourselves floating in space, looking down at our planet from far above. From this vantage point, we would see not just the blue marble of Earth itself, but also the vast, teardrop-shaped bubble of magnetic influence that surrounds it. This magnetosphere extends about 40,000 miles toward the Sun and streams out behind Earth for millions of miles. Like the tail of a comet, the magnetosphere is created by the interaction between Earth's magnetic field and the solar wind. That constant stream of charged particles flowing from the Sun at speeds of over 1 million miles per hour. When these particles encounter Earth's magnetic field, they're deflected and channeled around our planet, creating a complex three-dimensional structure that's constantly changing and evolving. This interaction between the solar, wind, and Earth's magnetic field creates what scientists call the magnetosphere-ionosphere system, a coupled system that extends from the edge of space down to about 50 miles above Earth's surface. This system plays a subtle but important role in maintaining the stability of our planet's rotation through several different mechanisms. First, the magnetosphere acts as a buffer between Earth and the variable solar wind. When the solar wind is strong, it compresses the magnetosphere, changing the distribution of magnetic field lines around our planet. When the solar wind is weak, the magnetosphere expands. These changes create tiny variations in the gravitational and magnetic forces acting on Earth, which can influence the planet's rotation in measurable ways. The solar wind itself varies dramatically. Over time, from the gentle breeze of a few 100,000 miles per hour during quiet periods to the raging storm of several million miles per hour during solar storms. These variations are caused by changes in the Sun's magnetic field and activity level, including solar flares and coronal mass ejections that can send massive clouds of charged particles hurtling toward Earth. When these solar storms hit Earth's magnetosphere, they can cause significant disturbances in our planet's magnetic field. The magnetosphere can be compressed to half its normal size, and the magnetic field lines can be twisted and reconnected in complex ways. These magnetic storms can last for days and have effects that ripple down through Earth's atmosphere to the surface during particularly strong magnetic storms. The interaction between the solar wind and Earth's magnetosphere can actually change the speed of our planet's rotation by tiny amounts. This happens because the magnetic field lines that connect our planet to the solar wind can act like elastic bands, stretching and snapping back in ways that transfer angular momentum between the solar wind and Earth's rotation. The effect is incredibly small. We're talking about changes measured in microseconds, but it demonstrates how Earth's rotation is influenced by forces that extend far beyond our planet's surface. Our planet doesn't spin in isolation. It's part of a complex system that includes the Sun, the solar wind, and the entire heliosphere, the bubble of space, dominated by the Sun's influence. The magnetosphere also plays a crucial role in protecting Earth's atmosphere from being stripped away by the solar wind. Without this protection, the charged particles from the Sun would gradually erode our atmosphere, eventually leaving Earth as barren as Mars. The fact that we still have a thick atmosphere after billions of years is testament to the effectiveness of our magnetic shield. This atmospheric protection is intimately connected to Earth's rotational stability. The atmosphere, as we've learned, carries angular momentum and can influence the planet's rotation through wind patterns and seasonal changes. If the atmosphere were gradually stripped away, Earth's rotation would slowly change as the mass distribution around the planet shifted. The magnetosphere also channels charged particles from the solar wind toward Earth's polar regions, where they interact with the upper atmosphere to create the aurora borealis and aurora australis, the northern and southern lights. These beautiful displays of light are actually visible evidence of the complex interaction between our planet's magnetic field and the solar wind. The aurora occur when charged particles from the solar wind follow Earth's magnetic field lines down into the upper atmosphere, where they collide with atoms and molecules in the air. These collisions cause the atoms to emit light, creating the dancing curtains of green, red, and blue light that we see in the polar skies. The aurora are most active during magnetic storms, when the interaction between the solar wind and Earth's magnetosphere is most intense. The location and intensity of the aurora provides scientists with valuable information about the state of Earth's magnetic field and its interaction with the solar wind. By studying the aurora, researchers can track changes in the magnetosphere and understand how these changes might affect Earth's rotation and other planetary processes. One of the most fascinating aspects of Earth's magnetosphere is how it varies over time. The magnetic field itself changes strength and direction over periods ranging from years to millions of years. Every few 100,000 years, Earth's magnetic field actually reverses, with the north and south magnetic poles switching places. During these reversals, the magnetic field can weaken dramatically, potentially allowing more solar wind particles to reach Earth's atmosphere. Scientists have found evidence of hundreds of these magnetic reversals in the geological record preserved in the magnetic orientation of rocks and sediments. The last reversal occurred about 780,000 years ago, and some researchers believe we might be approaching another one, as Earth's magnetic field has been weakening over the past few centuries. During a magnetic reversal, the weakened magnetic field would provide less protection from the solar wind, potentially allowing more atmospheric erosion and changing the way solar wind particles interact with Earth's rotation. The effects would be subtle but measurable, adding another layer to the complex web of forces that influence our planet's spin. The magnetosphere also interacts with Earth's ionosphere, the layer of the atmosphere between about 50 and 400 miles above the surface, where solar radiation ionizes atoms and molecules, creating a sea of charged particles. The ionosphere is influenced by both the magnetic field rising from Earth's core and the solar wind coming from space, creating a dynamic boundary layer that's constantly changing. Changes in the ionosphere can affect radio communications, satellite operations, and even GPS navigation systems, but they can also influence Earth's rotation in subtle ways. The ionosphere carries electric currents that interact with Earth's magnetic field, creating forces that can transfer angular momentum between the ionosphere and the solid Earth below. These ionospheric effects are particularly pronounced during magnetic storms, when the interaction between the solar wind and Earth's magnetosphere sends waves of energy down into the ionosphere. These waves can heat the ionosphere, change the distribution of charged particles, and alter the electric currents flowing through this layer of the atmosphere. The heating of the ionosphere during magnetic storms can cause the atmosphere to expand, increasing atmospheric drag on satellites and space stations. This expansion also changes the distribution of mass in Earth's atmosphere, which can affect the planet's moment of inertia and rotation rate by tiny amounts. Even more intriguingly, scientists have discovered that the ionosphere can actually ring like a bell when struck by particularly strong solar wind disturbances. These ionospheric oscillations, with periods of several minutes, can couple with oscillations in Earth's magnetic field and potentially influence the planet's rotation in ways that are still being studied. The magnetosphere and ionosphere also play important roles in Earth's electrical circuit. Our planet acts like a giant electrical generator, with the ionosphere serving as one terminal and the surface as the other. Electric currents flow constantly between these terminals, driven by the interaction between the solar wind, Earth's magnetic field, and the ionosphere. This global electrical circuit is influenced by everything from thunderstorms to solar activity. Lightning strikes around the world pump electrical energy into this system, while solar storms can dramatically alter the flow of current. These changes in Earth's electrical state can have subtle effects on the planet's rotation. Though the mechanisms are still not fully understood, the study of Earth's magnetosphere and its effects on planetary rotation is a relatively new field of science, enabled by satellites that can measure magnetic fields and particle flows in space with unprecedented precision. As our understanding of these systems improves, we're discovering that Earth's rotation is influenced by factors that extend far beyond our planet's surface, reaching deep into space and connecting our world to the broader solar system. Every time you take a breath, you're participating in one of the most remarkable balancing acts in the solar system. The air around us, that invisible ocean of gases that we move through every day, is not just sitting there quietly. It's spinning along with our planet, swirling in complex patterns that span continents and oceans, and playing a crucial role in keeping Earth balanced as it rotates through space. To understand how our atmosphere helps maintain Earth's rotational balance, imagine our planet as a figure skater spinning on ice. The skater's flowing costume represents Earth's atmosphere, and just as the costume follows the skater's movements, while also having its own complex motions, our atmosphere is both carried along by Earth's rotation and has its own intricate patterns of movement that can influence the planet's spin. The atmosphere extends from the surface up to about 600 miles above our heads, though most of its mass is concentrated in the first 30 miles. This might seem like a thin shell compared to Earth's 8,000-mile diameter, but the atmosphere contains enough mass to significantly influence our planet's rotation. The total mass of the atmosphere is about 5.5 quadrillion tons. That's 5 quadrillion, 500 trillion tons of air swirling around our planet. When Earth spins, it drags this massive atmosphere along with it through friction with the surface. But the atmosphere doesn't just passively follow the planet's rotation. It has its own complex patterns of movement, driven by the uneven heating of Earth's surface by the sun. These atmospheric motions can speed up or slow down, and when they do, they can transfer angular momentum to or from the solid Earth, causing tiny changes in the planet's rotation rate. The most dramatic example of this atmospheric influence occurs in the upper atmosphere, where the jet streams circle the planet at speeds of up to 200 miles per hour. These rivers of fast-moving air, at altitudes of 30,000 to 40,000 feet, carry enormous amounts of angular momentum. when the jet streams speed up. They're like a figure skater extending their arms. They carry more angular momentum, which means the solid Earth must spin slightly slower to conserve the total angular momentum of the system. These changes in Earth's rotation due to atmospheric effects are measurable and regular. During Northern Hemisphere winter, when the jet streams are strongest, Earth's rotation slows down by about 1.7 milliseconds per day. During summer, when the jet streams weaken, the rotation speeds up again. It's a seasonal breathing of our planet, a regular rhythm that's been going on for millions of years. The atmosphere also responds to changes in Earth's rotation in complex ways. When the planet spins faster or slower, it affects the force that causes moving objects to curve as they travel over Earth's spinning surface. This changes the behavior of wind patterns, ocean currents, and weather systems, which in turn can influence the planet's rotation in a feedback loop that scientists are still working to understand. One of the most fascinating aspects of this atmospheric influence is how it varies with altitude. The lower atmosphere, where we live and where most weather occurs, is closely coupled to Earth's surface through friction. The air near the ground is dragged along by the spinning Earth and generally moves at the same speed as the surface below it. But as we go higher in the atmosphere, the coupling between the air and the solid Earth becomes weaker. In the upper atmosphere, the air can move at different speeds than the surface, creating layers of atmosphere that rotate at slightly different rates. These differential rotations can create atmospheric waves and oscillations that propagate up and down through the atmosphere, carrying energy and angular momentum between different layers. The ionosphere, that layer of the atmosphere between about 50 and 400 miles above the surface, is particularly interesting in this regard. Here, the thin air is ionized by solar radiation, creating charged particles that can be influenced by Earth's magnetic field. The ionosphere can actually rotate faster or slower than the surface, driven by electric currents that flow through this layer of the atmosphere during magnetic storms. When the solar wind interacts strongly with Earth's magnetosphere, the ionosphere can be heated and stirred by waves of energy from space. This heating can cause the ionosphere to expand and change its rotation rate, which can influence the rotation of the layers below it through a process called atmospheric tidal coupling. The term atmospheric tides might seem confusing at first. After all, we usually think of tides as something that happens in the ocean. But the atmosphere experiences tides too, caused by the gravitational pull of the moon and sun, as well as by heating from solar radiation. These atmospheric tides create regular, predictable patterns of rising and falling air pressure that circle the globe every day. The atmospheric tides are much more complex than ocean tides, because the atmosphere is a three-dimensional fluid that can move vertically as well as horizontally. Solar heating creates thermal tides that peak at different times of day, while gravitational tides create patterns that are synchronized with the moon's position. These different tidal patterns interfere with each other, creating complex oscillations in atmospheric pressure and wind patterns. These atmospheric tides can influence Earth's rotation in subtle but measurable ways. When the tides cause the atmosphere to bulge outward from the planet, they change the distribution of mass in the atmosphere, which affects Earth's moment of inertia. When the atmosphere contracts, the effect is reversed. These changes happen on daily, monthly, and seasonal cycles, creating regular variations in Earth's rotation rate. The atmosphere also plays a crucial role in redistributing heat around the planet, which indirectly affects Earth's rotation. Without the atmosphere, the day side of Earth would be scorching hot, while the night side would be freezing cold. The atmosphere transports heat from the equator to the poles and from the day side to the night side, creating a more even temperature distribution. This heat redistribution is accomplished through complex patterns of atmospheric circulation. Warm air rises at the equator, flows toward the poles at high altitude, cools and sinks at higher latitudes, then flows back toward the equator at low altitude. This creates circulation cells that span thousands of miles and transport vast amounts of energy around the planet. These circulation patterns are influenced by Earth's rotation through the Coriolised effect, which causes moving air to curve to the right in the northern hemisphere and to the left in the southern hemisphere. The result is a complex pattern of trade winds, westerlies, and polar easterlies that circle the globe in bands. These wind patterns carry angular momentum and can influence Earth's rotation when they strengthen or weaken. The atmosphere also interacts with the oceans in complex ways that affect Earth's rotation. The wind patterns drive ocean currents, which carry heat and angular momentum around the planet. Changes in ocean currents can cause water to pile up in some regions and drain away from others, changing the distribution of mass on Earth's surface and affecting the planet's rotation. One of the most dramatic examples of this ocean-atmosphere interaction is the El Niño Southern Oscillation, a climate pattern that affects the entire Pacific Ocean. During El Niño events, changes in ocean temperature patterns alter wind patterns across the Pacific, which can affect the length of Earth's day by up to a millisecond. The effect is caused by changes in the angular momentum carried by both the atmosphere and the ocean. The atmosphere also plays a role in the exchange of angular momentum between different parts of Earth's system. When strong winds blow over mountains, they can create atmospheric waves that propagate up into the upper atmosphere. These waves can carry angular momentum from the surface to high altitudes, where it can be transferred to the ionosphere and potentially to space through interaction with the solar wind. Similarly, when the atmosphere is heated by solar radiation or cooled by radiation to space, it can expand or contract, changing its moment of inertia and affecting Earth's rotation. These thermal effects are most pronounced during solar storms, when increased solar radiation can heat the upper atmosphere and cause it to expand significantly. The study of how the atmosphere influences Earth's rotation is an active area of research, with scientists using computer models and satellite observations to understand these complex interactions. As our understanding improves, we're discovering that the atmosphere is not just a passive passenger on our spinning planet, but an active participant in maintaining the delicate balance that keeps Earth rotating steadily through space. The atmosphere also provides us with a record of Earth's rotational history. By studying the patterns of atmospheric circulation preserved in ice cores, tree rings, and other climate records, scientists can reconstruct how Earth's rotation has changed over thousands of years. These records show that Earth's rotation has been remarkably stable over long periods, with only tiny variations caused by changes in the atmosphere, oceans, and ice sheets. This stability is crucial for life on Earth. The regular cycle of day and night, the predictable patterns of seasons, and the stable climate that has allowed life to evolve and thrive. All of these depend on Earth's steady rotation. The atmosphere plays a key role in maintaining this stability, acting as a buffer that smooths out short-term variations and helps keep our planet spinning at a constant rate. As we continue to study the intricate dance between Earth's atmosphere and its rotation, we're gaining a deeper appreciation for the complex web of forces that keep our planet balanced. The atmosphere is not just the air we breathe, it's an integral part of the system that makes Earth a stable, habitable world. Every breath of wind, every storm, every seasonal change is part of this cosmic balancing act that has been going on for billions of years and will continue for billions more. As we venture deeper into our exploration of how Earth keeps its balance while spinning, we encounter a remarkable chapter in our planet's story that unfolds right before our eyes. This is the story of how our modern world has begun to influence the very dance of balance that has sustained our planet for billions of years. It's a gentle reminder that everything in our universe is connected, and even the smallest changes can ripple through the cosmic symphony of motion. Imagine, if you will, a figure skater performing a graceful spin on ice. When she extends her arms, she slows down slightly, and when she pulls them close to her body, she spins faster. This beautiful demonstration of physics happens because of something called the conservation of angular momentum. The same principle that governs how Earth maintains its rotational balance. Now, picture our planet as that elegant skater, and consider how the redistribution of mass across her surface might affect her spin. In recent decades, scientists have discovered something quite extraordinary. The way we use water, the melting of ice sheets, and even the construction of massive dams have begun to influence Earth's rotation in measurable ways. It's not dramatic like a sudden stumble, but rather like the subtle adjustments a dancer makes to maintain perfect balance. These changes speak to the incredible sensitivity of our planet's rotational system and remind us of the delicate interconnectedness of all Earth's systems. When we pump groundwater from deep aquifers, we're essentially moving mass from one part of our planet to another. The water that once rested deep underground eventually finds its way to the oceans, slightly altering the distribution of mass on Earth's surface. This redistribution, though seemingly small, can affect our planet's moment of inertia and, consequently, its rotational behavior. It's like watching a master clockmaker make the tiniest adjustment to ensure perfect timing. The great ice sheets of Greenland and Antarctica, those ancient frozen archives of Earth's climate history, are also participants in this delicate dance. As these massive ice formations respond to changing temperatures, they redistribute enormous amounts of mass. When ice melts and flows into the oceans, it's not just raising sea levels, it's also subtly altering Earth's rotational characteristics. The planet adjusts to these changes with the same graceful precision it has maintained for eons. But the adjustments are now happening at a pace that allows us to observe and measure them. Perhaps most fascinating is how these changes reveal the incredible sensitivity of Earth's rotational system. The fact that we can detect these subtle variations in our planet's spin speaks to both the precision of our modern instruments and the remarkable stability of Earth's rotation. It's like being able to hear the softest whisper in a vast concert hall, a testament to the quietude of our planet's normal rotational behavior. Let us turn our attention to one of the most dynamic participants in Earth's rotational ballet, our atmosphere. The vast envelope of air that surrounds our planet is far from static. It breathes, it flows, it dances with the seasons, and in doing so, it plays a crucial role in how Earth maintains its balance while spinning. This atmospheric dance is one of the most beautiful examples of how seemingly separate systems work together in perfect harmony. Think of Earth's atmosphere as a vast, invisible ocean of air, constantly in motion. Just as ocean currents redistribute water around the globe, atmospheric currents redistribute air masses, and with them, angular momentum. When strong winds blow from west to east, they can actually speed up Earth's rotation by a tiny amount. When they blow from east to west, they can slow it down. It's as if the atmosphere is engaged in a constant, gentle conversation with the solid Earth beneath it, sometimes giving it a little push, sometimes holding it back. The seasonal changes we experience are part of this atmospheric dance. During different times of the year, the global circulation patterns shift, the jet streams meander, and the distribution of air masses changes. These changes can cause minute variations in the length of our day, variations so small that they're measured in milliseconds, but significant enough to reveal the intimate connection between our weather systems and our planet's rotation. One of the most remarkable aspects of this atmospheric influence is how it demonstrates the principle of conservation of angular momentum on a planetary scale. When the atmosphere speeds up in one direction, something else must slow down to compensate. That something is often the solid Earth itself. This exchange of angular momentum between different parts of our planet is happening constantly, creating a dynamic equilibrium that maintains the overall balance of the Earth-nosphere system. The El Niño and La Niña phenomena provide beautiful examples of how atmospheric changes can influence Earth's rotation. During these climate oscillations, the patterns of atmospheric circulation across the Pacific Ocean change dramatically. The shifting trade winds and altered weather patterns can cause measurable changes in Earth's rotational speed. It's like watching a planetary scale demonstration of how interconnected our world truly is. Even the daily heating and cooling of our atmosphere plays a role in this dance. As the sun rises and sets, the atmosphere expands and contracts, creating pressure waves that travel around the globe. These atmospheric tides, much like ocean tides, exert subtle but measurable influences on Earth's rotation. The planet responds to these rhythmic changes with the same precision it has maintained for billions of years, adjusting its spin to maintain perfect balance. The study of these atmospheric influences has revealed something profound about our planet's rotational stability. Despite all these constant changes and perturbations, Earth maintains its spin with remarkable consistency. The variations we observe are tiny compared to the overall rotational motion, demonstrating the incredible stability of our planet's rotational system. It's as if Earth has an internal compass that always knows how to find its way back to perfect balance. As we continue our gentle exploration of how Earth keeps its balance while spinning, we encounter one of the most poetic aspects of our planet's rotational story, the gradual lengthening of our days. This is a story that unfolds over such vast timescales that it speaks to the patience of geological processes and the enduring nature of celestial mechanics. It's a reminder that even the most stable systems in our universe are subject to the gentle passage of time. The moon, that faithful companion that has watched over Earth for billions of years, continues to play a crucial role in this slow transformation. Through the mechanism of tidal friction, the moon is gradually stealing energy from Earth's rotation, causing our planet to spin just a little bit slower with each passing year. This process is so gradual that it's imperceptible in human timescales. But over geological time, it has profoundly shaped both Earth and the moon. Imagine, if you will, traveling back in time to witness Earth's early days. You would find a world spinning much faster than today, with days lasting perhaps only 6 hours. The moon would appear much larger in the sky, orbiting much closer to Earth. The tidal forces would be dramatically stronger, creating massive tidal bores that would sweep across the continents. it would be a world of intense energy and rapid change. Yet even then, the same fundamental principles that govern Earth's balance today were already at work. As eons passed, this energetic system gradually evolved into the more serene configuration we know today. The moon slowly drifted away from Earth, its gravitational influence weakening but never disappearing. Earth's rotation slowed, but in a way that maintained the delicate balance necessary for stable climate and orbital mechanics. It's a beautiful example of how systems can evolve while maintaining their essential character. The evidence for this gradual change is written in the rocks themselves. Ancient coral reefs, those living calendars of the past, show growth patterns that reveal the length of ancient days. By counting the daily growth rings in fossilized corals, scientists can determine that days were indeed shorter in the past. It's like reading a story written in stone, a narrative that spans hundreds of millions of years. This gradual lengthening of our days also affects other aspects of Earth's rotational behavior. As the planet spins more slowly, its equatorial bulge gradually decreases, affecting the distribution of mass and, consequently, the precession of Earth's axis. These changes are interconnected, each influencing the others in a complex web of gravitational relationships that maintains the overall stability of our planet's orientation in space. What's particularly remarkable is how this gradual change doesn't destabilize Earth's rotation, but rather represents a slow evolution toward a new equilibrium. The same principles that have kept Earth balanced throughout its history continue to operate, adapting to the changing conditions while maintaining the essential characteristics that make our planet habitable. It's a testament to the robustness of the physical laws that govern planetary motion. Deep beneath our feet, in the molten heart of our planet, another participant in Earth's rotational ballet performs its ancient dance. The liquid iron core of Earth, that vast sphere of molten metal that generates our planet's magnetic field, has its own complex relationship with Earth's rotation. This relationship is so intricate and profound that it continues to surprise and delight scientists who study the deep dynamics of our planet. Picture, if you can, a sphere of liquid metal, heated to temperatures that would melt rock, spinning within the solid mantle that surrounds it. This is not a simple, uniform rotation, but a complex, swirling motion driven by convection currents and influenced by the Coriolis effect. The liquid core can speed up or slow down relative to the mantle, creating a dynamic system that exchanges angular momentum between different parts of our planet. This core-mantle interaction is like a cosmic dance between partners, where sometimes one leads and sometimes the other. When the liquid core speeds up, it can transfer angular momentum to the mantle, causing subtle changes in Earth's rotation rate. When it slows down, the opposite happens. These exchanges occur over timescales ranging from years to decades, creating variations in Earth's rotation that scientists have only recently begun to understand. One of the most beautiful aspects of this deep Earth process is how it demonstrates the principle of conservation of angular momentum on a planetary scale. The total angular momentum of the Earth system remains constant, but it can be redistributed between different parts of the planet. When the core gains angular momentum, the mantle loses an equivalent amount, and vice versa. It's like watching a perfectly balanced seesaw, where the total balance is maintained even as the distribution changes. The magnetic field that protects us from harmful solar radiation is intimately connected to this deep rotational dynamics. The complex motions in the liquid core that generate Earth's magnetic field are influenced by the planet's rotation, and in turn, they influence the rotation through electromagnetic coupling with the mantle. It's a beautiful example of how different physical processes can work together to maintain planetary stability. Scientists have discovered that the inner core, that solid sphere of iron and nickel at the very center of our planet, may rotate at a slightly different rate than the rest of Earth. This differential rotation, if it exists, would represent another layer of complexity in Earth's rotational system. It would mean that our planet is not a single, rigid body, but rather a complex system of interacting parts, each with its own rotational characteristics. The study of these deep Earth processes has revealed something profound about our planet's rotational stability. Despite all the complex interactions occurring deep within Earth, the planet maintains its overall rotational balance with remarkable consistency. The variations we observe are small compared to the overall motion, demonstrating the incredible stability of the system as a whole. It's as if Earth has an internal gyroscope that helps it maintain its balance, no matter what's happening in its deep interior. As our journey through the mechanisms of Earth's rotational balance continues, we encounter some of the most subtle and beautiful aspects of our planet's motion. These are the small oscillations and wobbles that Earth performs as it spins. Tiny variations that reveal the incredible precision with which our planet maintains its balance. Like a master musician adding subtle variations to a beautiful melody. Earth's rotation includes these gentle oscillations that speak to the complexity and elegance of planetary motion. The Chandler wobble, named after the American astronomer who first observed it, is perhaps the most famous of these oscillations. This is a slight wobble in Earth's axis of rotation, with a period of about 433 days. It's as if Earth is performing a slow, graceful dance, swaying gently as it spins. The amplitude of this wobble is tiny, only a few meters at Earth's surface, but it's regular and persistent, like the gentle swaying of a tree in a soft breeze. What causes this beautiful wobble? It's the result of Earth not being a perfect sphere, but rather an oblate spheroid with a slight bulge at the equator. When the axis of rotation doesn't align perfectly with the axis of symmetry, the planet wobbles slightly as it spins. This wobble is maintained by various factors, including changes in atmospheric pressure, ocean currents, and even the movement of groundwater. It's a delicate balance of forces that creates this persistent oscillation. The annual wobble is another of these gentle oscillations, caused by the seasonal redistribution of mass as water moves between the oceans and continents, and as atmospheric patterns change with the seasons. This wobble has a period of exactly 1 year, synchronized with Earth's journey around the Sun. It's like Earth is keeping time with the cosmic calendar, adjusting its rotation slightly to acknowledge the changing seasons. These oscillations are measured using techniques that would seem almost magical to previous generations. Scientists use very long baseline interferometry, a technique that measures the tiny changes in Earth's orientation by observing distant quasars, those incredibly bright objects at the edge of the observable universe. By tracking the apparent positions of these cosmic lighthouses, researchers can detect changes in Earth's rotation that are smaller than the width of a human hair at the planet's surface. What's remarkable about these oscillations is how they demonstrate Earth's incredible stability, despite all the complex forces acting on our planet. Despite the constant changes in the distribution of mass due to weather, ocean currents, and geological processes, Earth maintains its rotational balance with extraordinary precision. The oscillations are tiny variations around a fundamentally stable state, like the gentle swaying of a well-balanced top. The study of these oscillations has practical applications as well. Understanding Earth's rotation variations is crucial for maintaining accurate timekeeping, for precise navigation, and for the operation of satellites and space missions. It's a beautiful example of how fundamental scientific research into the nature of our planet's motion has direct applications in our daily lives. As we look toward the future, we can imagine how Earth's rotational balance might continue to evolve. The same principles that have governed our planet's motion for billions of years will continue to operate, but the conditions under which they operate will gradually change. It's like watching a long, slow dance that continues to unfold, with new movements developing while the underlying choreography remains constant. The moon will continue its slow drift away from Earth, gradually reducing the tidal forces that have shaped our planet's rotation throughout its history. This process will continue for billions of years, eventually leading to a state where Earth and the moon are tidally locked to each other, with the same face of each body always facing the other. It would be a cosmic dance of perfect synchronization, a testament to the power of gravitational forces to create order from chaos. Climate change will likely continue to influence Earth's rotation in subtle ways, as ice sheets melt and sea levels rise, as atmospheric circulation patterns shift, and as the distribution of water around the globe changes. Earth will continue to make tiny adjustments to maintain its rotational balance. These changes will be evidence of our planet's remarkable adaptability, its ability to respond to changing conditions while maintaining its essential stability. Technological advances will undoubtedly provide us with even more precise measurements of Earth's rotation and the factors that influence it. We may discover new oscillations, new coupling mechanisms between different parts of the Earth's system, and new insights into the deep dynamics of our planet. Each new discovery will add another layer to our understanding of how Earth maintains its balance while spinning. The study of Earth's rotation also provides insights into the rotation of other planets and the dynamics of planetary systems beyond our own. As we discover more exoplanets and learn about their characteristics, our understanding of Earth's rotational behavior helps us interpret the behavior of worlds orbiting distant stars. It's a beautiful example of how studying our own planet can illuminate the broader universe. Perhaps most importantly, our growing understanding of Earth's rotational dynamics reminds us of the incredible interconnectedness of all Earth's systems. The rotation of our planet is influenced by the atmosphere, the oceans, the solid Earth, and even the activities of life itself. This interconnectedness suggests that, as we face environmental challenges, we must consider how our actions might affect not just individual systems, but the planet as a whole. The future of Earth's rotational balance will likely be characterized by the same remarkable stability that has characterized it throughout our planet's history. Despite all the changes and perturbations that will occur, Earth will continue to spin with the same precision and grace that has made it a stable platform for life for billions of years. It's a reminder that even in a universe of constant change, some things endure with beautiful consistency. As our exploration of how Earth keeps its balance while spinning draws toward a close, we find ourselves reflecting on the profound wisdom embedded in the ancient rhythms of our planet. These rhythms, established over billions of years of evolution, represent a kind of planetary intelligence, a deep understanding of how to maintain balance in the face of constant change. They remind us that stability and change are not opposites, but rather partners in the cosmic dance of existence. The rotational systems we've explored throughout our journey are examples of what scientists call dynamical systems, complex networks of interacting components that maintain their overall behavior through feedback mechanisms and conservation laws. Earth's rotation is stable not because it's rigid and unchanging, but because it's flexible and responsive, able to adapt to changing conditions while maintaining its essential characteristics. This flexibility is perhaps most beautifully demonstrated in how Earth responds to the various forces that could potentially destabilize its rotation. When tidal forces try to slow the planet's spin, Earth adjusts its internal dynamics to maintain stability. When atmospheric changes try to alter its rotation rate, the planet redistributes angular momentum to compensate. When geological processes shift masses around, Earth modifies its rotational characteristics to maintain balance. The timescales involved in these processes span from milliseconds to billions of years, creating a hierarchy of stability that operates at multiple levels. Short-term variations are accommodated by atmospheric and oceanic adjustments. Medium-term changes are handled by the coupling between different parts of the Earth's system. Long-term evolution is governed by the fundamental conservation laws of physics. It's like a complex musical composition with rhythms nested within rhythms, each contributing to the overall harmony. This multi-scale stability offers profound lessons for how we might approach the challenges facing our modern world. Just as Earth maintains its rotational balance through flexibility and responsiveness rather than rigidity, perhaps our human systems could benefit from similar approaches. The planet's ability to maintain stability while accommodating change suggests that resilience comes not from resistance to change, but from the ability to adapt while maintaining core principles. The study of Earth's rotational dynamics also reveals the importance of understanding systems as wholes rather than collections of parts. Each component of Earth's rotational system, the solid Earth, the atmosphere, the oceans, the moon, influences all the others. The behavior of the whole system emerges from these interactions and cannot be understood by studying each part in isolation. It's a reminder that in our interconnected world, systems thinking is essential for understanding complex phenomena. Perhaps most importantly, our exploration of Earth's rotational balance reveals the incredible precision and elegance of the physical laws that govern our universe. The same principles that keep Earth spinning smoothly also govern the motion of atoms, the behavior of galaxies, and the evolution of the cosmos itself. There's a deep unity in the laws of physics, a consistency that allows the same mathematical principles to describe phenomena across vast scales of space and time. As we near the end of our journey through the mechanisms of Earth's rotational balance, we must acknowledge one of the most remarkable aspects of our planet's story, the role of life itself in maintaining the conditions necessary for continued habitability. Earth is not just a spinning ball of rock and metal, but a living planet where biological processes interact with physical systems in ways that continue to surprise and inspire scientists. The stability of Earth's rotation has been crucial for the development and maintenance of life on our planet. The regular cycle of day and night, the stability of the seasons, the consistency of our planet's orientation in space, all of these factors have provided the stable environmental conditions necessary for life to flourish. In turn, life has influenced these very systems, creating a complex web of interactions between the biological and physical worlds. Consider how the evolution of photosynthesis changed Earth's atmosphere, affecting atmospheric circulation patterns, and, consequently, the planet's rotational dynamics. The rise of oxygen in the atmosphere altered the chemistry of the oceans, influenced the formation of clouds, and changed the way energy is distributed around the planet. These changes, while subtle, have had cascading effects on the systems that maintain Earth's rotational balance. The formation of massive limestone deposits by marine organisms has redistributed enormous amounts of carbon around the planet, slightly altering Earth's mass distribution and moment of inertia. The growth of forests has influenced atmospheric circulation patterns, while the formation of soil has affected the distribution of water and the stability of continents. Each of these biological processes has contributed to the complex system that maintains Earth's rotational stability. Perhaps most remarkably, the emergence of human civilization has introduced new factors into Earth's rotational dynamics. The construction of massive dams, the extraction of groundwater, the redistribution of materials through agriculture and industry, all of these activities have begun to influence our planet's rotation in measurable ways. We have become, in a sense, a geological force, capable of affecting the same planetary systems that have operated for billions of years. This realization brings with it both wonder and responsibility. The fact that our activities can influence something as fundamental as Earth's rotation speaks to the incredible sensitivity of planetary systems and the interconnectedness of all things on Earth. It reminds us that we are not separate from the natural world, but deeply embedded within it, participants in the same cosmic dance that has been unfolding for billions of years, looking toward the future. We can envision how life might continue to influence Earth's rotational dynamics as we develop new technologies and change the way we interact with our planet. We must consider how these changes might affect the delicate balance that has sustained life for so long. The story of Earth's rotation is also the story of life itself, and we are now active participants in writing the next chapter of that story. The living planet perspective reminds us that Earth's rotational balance is not just a matter of physics and astronomy, but also a matter of biology and ecology. The systems that keep our planet spinning smoothly are the same systems that support life, and life, in turn, helps maintain these systems. It's a beautiful example of the self-regulating nature of our planet, the way different processes work together to maintain the conditions necessary for continued existence. As we step back to view Earth's rotational balance from a cosmic perspective, we begin to appreciate how remarkable our planet's stability really is. In the vast cosmos, with its black holes, exploding stars, and chaotic gravitational interactions, Earth represents an island of stability and predictability. Our planet's ability to maintain its rotational balance while navigating the complexities of the solar system is a testament to the fundamental order that underlies apparent chaos. The solar system itself is a complex gravitational dance, with planets, moons, asteroids, and comets all influencing each other through their gravitational fields. Earth must maintain its rotational balance while participating in this cosmic ballet, responding to the gravitational tugs of other planets, while maintaining its own internal stability. It's like a dancer performing a solo, while surrounded by other dancers, each creating their own patterns and rhythms. Jupiter, that giant guardian of the outer solar system, plays a particularly important role in maintaining Earth's rotational stability. Its massive gravitational field helps deflect comets and asteroids that might otherwise collide with Earth, preventing catastrophic impacts that could drastically alter our planet's rotation. Jupiter's presence also helps stabilize the orbits of the inner planets, maintaining the predictable celestial mechanics that allow Earth to maintain its regular cycles. The Sun, our nearest star, is the ultimate source of energy that drives many of the processes that influence Earth's rotation. Solar heating creates the atmospheric circulation patterns that exchange angular momentum with the solid Earth. Solar radiation powers the water cycle that redistributes mass around the planet. Even the solar wind, that stream of charged particles flowing from the sun, interacts with Earth's magnetic field in ways that can influence our planet's rotational dynamics. From this cosmic perspective, we can see how Earth's rotational balance is not an isolated phenomenon, but part of a larger pattern of stability and order in the universe. The same physical laws that govern Earth's rotation also govern the motion of stars, the evolution of galaxies, and the expansion of the universe itself. There's a deep unity in the cosmos, a consistency in the laws of physics that allows the same principles to operate across all scales of space and time. This cosmic view also reminds us of the rarity and preciousness of Earth's stability. While we've discovered thousands of exoplanets orbiting other stars, we haven't yet found another world that exhibits the same kind of long-term rotational stability that characterizes Earth. Our planet's balance is the result of a unique combination of factors: its size, its distance from the sun, the presence of the moon, the composition of its atmosphere that may be rare in the universe. The search for exoplanets has revealed worlds with extreme rotational behaviors, planets that are tidally locked to their stars, worlds that tumble chaotically through space, and systems where planets' rotations are constantly perturbed by nearby stellar companions. Against this backdrop of cosmic diversity, Earth's steady, predictable rotation appears even more remarkable and precious. Understanding Earth's rotational balance also helps us appreciate the conditions necessary for life as we know it. The stability of our planet's rotation has been crucial for maintaining the regular cycles of day and night, the predictability of seasons, and the long-term stability of climate patterns. These conditions have provided the stable environment necessary for life to evolve and flourish over billions of years. As our gentle exploration of how Earth keeps its balance while spinning approaches its conclusion, we find ourselves marveling at the eternal nature of the cosmic dance in which our planet participates. This is a dance that began with the formation of the solar system over 4.5 billion years ago, and it will continue long after the last star has burned out in the distant future. It's a dance of such grace and precision that it speaks to the fundamental harmony underlying all existence. The mechanisms we've explored throughout our journey, the gyroscopic effects, the tidal forces, the atmospheric interactions, the deep Earth dynamics, all work together in a symphony of motion that has sustained our planet through countless changes and challenges. Ice ages have come and gone, continents have drifted across the globe, the atmosphere has been transformed by life, yet through it all, Earth has maintained its rotational balance with remarkable consistency. This consistency is not static, but dynamic. It's the consistency of a river that always flows, yet is never the same. The consistency of a flame that burns steadily while its substance constantly changes. Earth's rotational balance is maintained not through rigidity, but through flexibility, not through resistance to change, but through the ability to adapt while maintaining essential characteristics. The timescales involved in this cosmic dance span from the instantaneous to the eternal. Atmospheric variations affect Earth's rotation on timescales of days and months. Tidal forces operate over thousands and millions of years. The evolution of the Earth-Moon system unfolds over billions of years. Each timescale contributes to the overall stability of the system. creating a hierarchy of balance that operates at multiple levels simultaneously. Perhaps most remarkably, this eternal dance is not a solo performance, but a collaborative effort, involving every component of the Earth's system. The solid Earth, the oceans, the atmosphere, the moon, and even life itself all contribute to maintaining the rotational balance that has made our planet a stable home for life. It's a reminder that in the deepest sense, we are all participants in this cosmic dance, not observers standing outside it. The study of Earth's rotational balance reveals something profound about the nature of stability in the universe. True, stability is not the absence of change, but the ability to maintain essential characteristics while adapting to changing conditions. Earth's rotation is stable not because it's unchanging, but because it's capable of accommodating change while maintaining its fundamental character. This insight has implications that extend far beyond the realm of planetary science. In our personal lives, in our communities, in our approach to global challenges, we might learn from Earth's example. The planet's ability to maintain balance through flexibility rather than rigidity, through adaptation rather than resistance, suggests that resilience comes not from avoiding change, but from learning to dance with it. The eternal nature of Earth's rotational dance also reminds us of our place in the cosmos. We are temporary participants in a story that began long before. We existed and will continue long after we're gone. Yet our participation is meaningful, for we are the first species on Earth to understand the mechanisms that keep our planet spinning smoothly. And with that understanding comes both wonder and responsibility. As we conclude our peaceful journey through the mechanisms of how Earth keeps its balance while spinning, we're left with a profound sense of wonder and gratitude. The story we've explored together is not just about physics and astronomy, but about the fundamental nature of existence itself. It's a story that reveals the incredible elegance and precision of the laws that govern our universe, and the remarkable stability that emerges from the apparent chaos of countless interacting forces. The gift of understanding Earth's rotational balance is also the gift of understanding our own place in the cosmos. We are not separate from the planet that sustains us, but deeply embedded within its systems. The same forces that keep Earth spinning smoothly also flow through our bodies, govern the behavior of our cells, and influence the patterns of our thoughts. We are, in the most literal sense, children of the Earth, formed from the same materials and governed by the same laws that maintain our planet's balance. This understanding brings with it a sense of responsibility. As we've seen throughout our journey, even small changes can have significant effects on Earth's rotational dynamics. The activities of human civilization, while tiny compared to the vast forces that govern planetary motion, are beginning to influence the same systems that have maintained Earth's stability for billions of years. This influence is both a testament to our power and a reminder of our responsibility to be thoughtful stewards of the systems that sustain us. The story of Earth's rotational balance also offers hope for the future. Despite all the changes and challenges our planet has faced throughout its history, it has maintained its essential stability and continued to provide a suitable environment for life to flourish. The same principles that have sustained Earth through countless changes will continue to operate in the future, adapting to new conditions while maintaining the fundamental characteristics that make our planet habitable. Perhaps most importantly, our exploration of Earth's rotational balance reminds us of the interconnectedness of all things. The rotation of our planet is influenced by the atmosphere, the oceans, the solid Earth, the moon, and even the activities of life itself. This interconnectedness suggests that our actions, no matter how small they might seem, are part of a larger web of relationships that extends throughout the Earth system and beyond. The precision and elegance of Earth's rotational balance also speak to the fundamental beauty of the physical laws that govern our universe. The same mathematical principles that describe the motion of our planet also describe the behavior of atoms, the evolution of stars, and the expansion of the cosmos. There's a deep unity in the laws of physics, a consistency that allows the same principles to operate across all scales of space and time as we carry the insights from our journey forward into our daily lives. We might remember that we are participants in the same cosmic dance that keeps Earth spinning smoothly. The stability and grace of our planet's rotation can inspire us to seek similar qualities in our own lives. The ability to maintain balance while adapting to change, the wisdom to understand our place in larger systems, and the grace to move through life with the same elegance that characterizes planetary motion. The story of how Earth keeps its balance while spinning is ultimately a story of hope, resilience, and enduring beauty. It reminds us that even in a universe of constant change, some things endure with remarkable consistency. It suggests that stability and change are not opposites, but partners in the cosmic dance of existence. And it offers us a model for how we might live our own lives with balance, grace, and deep appreciation for the interconnected systems that sustain us all. Thank you for staying with me through this peaceful journey into the fascinating world of how Earth keeps its balance while spinning. I hope that our exploration together has brought you a sense of wonder about the remarkable planet we call home, and perhaps a deeper appreciation for the incredible precision and elegance of the natural world. As you go about your daily life, remember that you are part of this cosmic dance, a participant in the same eternal story that keeps our planet spinning smoothly through the vast reaches of space. The universe is filled with beauty and mystery, and we are blessed to be conscious beings, capable of understanding and appreciating the incredible systems that sustain us. May this understanding bring you peace, wonder, and a deep sense of connection to the magnificent cosmos of which we are all a part. If you've enjoyed this gentle exploration of Earth's rotational balance, I invite you to continue your journey of discovery. The natural world is filled with countless other stories of equal beauty and wonder, each offering its own insights into the incredible complexity and elegance of existence. Whether you're gazing at the stars, feeling the wind on your face, or simply watching the sun rise and set, remember that you are witnessing the same cosmic dance that has sustained our planet for billions of years. The universe is vast and mysterious, but it is also our home, and we are part of its ongoing story of beauty, balance, and endless possibility.